Imagine holding a teaspoon, just an ordinary teaspoon, the kind you might use to stir your morning coffee or measure out sugar for a recipe. Now imagine that teaspoon filled with material from the surface of a neutron star. That single teaspoon would weigh approximately 6 billion tons, not million, billion. That is more than the combined weight of every car, truck, ship, airplane, and train on Earth. Every vehicle humanity has ever built, compressed into a space you could hold between your thumb and forefinger. If you could somehow bring that teaspoon to Earth, you could not hold it. No human arm could support such weight. No floor could bear it. The teaspoon would fall through your hand as if your flesh were made of mist. It would punch through the floor, through the foundation, through the bedrock beneath. It would tunnel through the Earth itself, pulled by gravity so intense that nothing could stop its descent. That teaspoon would oscillate back and forth through the planet's core until friction finally brought it to rest at the center of the Earth, having carved a tunnel of destruction through miles of rock and metal. And here is the remarkable thing. That teaspoon contains material from the surface of a neutron star. The outer layer, the relatively normal part. Deeper inside these objects, the density climbs higher still, reaching conditions so extreme that our language struggles to describe them and our mathematics strains to calculate them. These objects should not exist. Physics seems to forbid them at every turn. Matter should not compress so tightly. Atoms should not survive such crushing pressure. Magnetic fields should not reach such terrifying intensities. Objects should not spin so fast without tearing themselves apart. And yet neutron stars are out there right now, thousands of them scattered across our galaxy alone, spinning in the darkness between stars, defying everything we thought we understood about the limits of matter and energy. Tonight, we are going to explore these impossible objects. We are going to journey from the violent deaths of massive stars to the strangest states of matter in the universe. We are going to witness explosions that outshine entire galaxies and collisions that forge gold from nuclear fire. We are going to push our understanding to its limits and then peer over the edge into mysteries that remain unsolved. A neutron star, at its most basic level, is the collapsed core of a dead massive star. When certain stars exhaust their nuclear fuel and die, they do not fade away quietly. They explode with unimaginable violence, blasting their outer layers across space while their cores collapse inward under the crushing force of their own gravity. What remains is an object so dense, so compact, so extreme that it exists on the knife's edge between matter and oblivion. Consider the fundamental contradiction that a neutron star represents. It is matter compressed so tightly that atoms themselves cease to exist in any recognizable form. In your body right now, atoms maintain their structure. Electrons orbit nuclei at relatively vast distances, like planets orbiting the sun with mostly empty space between them. In a neutron star, that empty space has been crushed out of existence. The electrons have been forced into the atomic nuclei, combining with protons to form neutrons. What remains is not atoms in any conventional sense. It is nuclear matter, a solid mass of neutrons packed together like marbles in a jar, with no empty space between them. This should not be stable. Quantum mechanics tells us that particles resist being confined to small spaces. The closer you push particles together, the more violently they push back. This is not a force in the conventional sense, but a consequence of the Heisenberg uncertainty principle, one of the foundational laws of quantum physics. And yet in neutron stars, gravity wins. The crushing weight of a stellar mass compressed into a city-sized sphere is enough to overcome even quantum resistance, forcing particles into configurations that seem impossible. The temperature should make things even worse. The surface of a neutron star glows at temperatures exceeding 500,000 degrees, hot enough to vaporize any known material. The core is hotter still, perhaps hundreds of billions of degrees in newly formed neutron stars. At such temperatures, matter should be a plasma, a chaotic soup of particles flying apart. Instead, neutron star matter forms structures. It has a crust. It may have layers. Deep inside, it may contain states of matter that exist nowhere else in the universe. The magnetic fields present another impossibility. A typical neutron star has a magnetic field roughly 100 million to 1 trillion times stronger than Earth's magnetic field. Some neutron stars, called magnetars, have fields thousands of times stronger still, reaching intensities of 1 million billion times Earth's field. At such strengths, the magnetic field fundamentally alters the behavior of matter and even empty space itself. Atoms become elongated into needle shapes. Light bends in ways that seem to violate common sense. The vacuum itself becomes birefringent, meaning it bends different polarizations of light differently, as if empty space had suddenly transformed into a crystal. And then there is the rotation. When massive stars collapse to form neutron stars, they spin up dramatically, like ice skaters pulling in their arms. Some neutron stars rotate dozens of times per second. The fastest known neutron star spins 716 times every second. Its surface moves at roughly 1/4 the speed of light. Any object spinning that fast should fly apart. The centrifugal force should overcome whatever holds it together, but the gravity of a neutron star is so intense that it holds the star together against forces that would shred any ordinary object instantly. Imagine compressing the entire human population of Earth into a single sugar cube. Now imagine that sugar cube spinning 700 times per second. Now imagine it glowing with the heat of 1 million furnaces while generating magnetic fields strong enough to erase every computer hard drive on the planet from halfway across the solar system. You have begun to approach what a neutron star actually is. We are going to explore all of this tonight. We will start with fundamentals, examining how stars die and why some of those deaths produce these impossible objects. We will descend through the layers of a neutron star, from its thin atmosphere to its mysterious core, encountering states of matter that challenge our understanding at every depth. We will explore pulsars, the rotating neutron stars that sweep beams of radiation across the cosmos like cosmic lighthouses. We will meet magnetars, the most magnetic objects in existence, capable of affecting Earth's atmosphere from the other side of the galaxy. We will witness what happens when two neutron stars collide, an event so violent that it ripples space-time itself while forging the heavy elements that make up jewelry and electronics and parts of your own body. We will trace the boundary between neutron star and black hole, exploring the knife's edge where the densest matter that can exist gives way to the ultimate collapse. We will examine what neutron stars teach us about physics at its most extreme and confront the mysteries that remain unsolved after more than 50 years of study. The scale of what we are discussing defies human intuition. A neutron star is typically only 12 to 15 miles across, roughly the diameter of a modest city. If you placed a neutron star next to Manhattan, it would not look particularly large. You could drive across a neutron star in perhaps 20 minutes at highway speeds, assuming your car could somehow survive the journey. And yet that city-sized sphere contains more mass than our entire sun, which is itself large enough to fit 1.3 million Earths inside it. The sun is so large that it takes light, the fastest thing in the universe, over 4 seconds to travel from one side to the other. A neutron star contains more mass than that. Squeezed into a ball you could jog across in an afternoon. The density numbers become almost meaningless when you try to comprehend them. Water has a density of 1 gram per cubic centimeter. Lead is about 11 times denser. Gold is roughly 19 times denser than water. The core of our sun, where nuclear fusion generates the energy that lights our world, has a density of about 150 grams per cubic centimeter. A white dwarf star, the dense remnant left when stars like our sun die, reaches densities of roughly 1 million grams per cubic centimeter, already almost beyond imagination. A neutron star reaches densities of 400 billion grams per cubic centimeter. If you could somehow scoop out a cubic centimeter of neutron star material, roughly the size of a small dice, it would weigh 400 million tons. A thimbleful would outweigh a mountain. A handful would outweigh the asteroid that killed the dinosaurs. These numbers do not fit in human minds that evolved to estimate the weight of fruit and stones and other human beings. The first hints that such objects might exist came not from observation, but from theory. In 1934, Astronomers Walter Baade and Fritz Zwicky proposed that supernova explosions might produce extremely compact stars composed primarily of neutrons. The neutron itself had only been discovered 2 years earlier. Baade and Zwicky were speculating about objects that no one had ever seen and that seemed to push physics beyond any reasonable limit. Most astronomers filed the idea away as an interesting curiosity that might or might not prove relevant to the actual universe. It took another 33 years for neutron stars to transform from theoretical curiosity to observed reality. In 1967, a graduate student named Jocelyn Bell Burnell was analyzing data from a radio telescope in Cambridge, England. She noticed something strange in the data, a regular pulsing signal that repeated every 1.337 seconds with extraordinary precision. The pulses were so regular that they seemed artificial. The first interpretation considered seriously was that these might be signals from an extraterrestrial civilization. The source was half-jokingly designated LGM-1 for Little Green Men. But then Bell Burnell found a second pulsing source in a completely different part of the sky, with a different period but the same uncanny regularity. If these were alien signals, it would mean 2 separate civilizations happened to be broadcasting toward Earth with nearly identical technology. That seemed far less likely than some unknown natural phenomenon. The puzzle was solved when theorist Thomas Gold proposed that the signals came from rapidly rotating neutron stars, their beams of radiation sweeping across Earth like lighthouse beams sweeping across a dark ocean. We will return to this discovery story later, exploring how these cosmic lighthouses work and what they have taught us about the universe. But for now, settle in and get comfortable. This will be a long journey through some of the most extreme physics in the universe. If your mind wanders at times, if you drift in and out of attention, that is perfectly fine. The neutron stars will still be there. They have been spinning for millions of years. They can wait for you. Let us begin at the beginning, with the death of stars. Stars are battlegrounds. Every star in the night sky, including our own sun, exists in a state of perpetual conflict between 2 fundamental forces. Gravity wants to crush the star into the smallest possible point. The star's own energy production pushes back, generating enough outward pressure to hold the star up against gravitational collapse. For millions or billions of years, this battle remains perfectly balanced. Neither side wins. The star simply exists, converting matter into energy, holding itself up through its own internal fire. The fuel that powers this resistance is nuclear fusion. In the core of a star like our Sun, the temperature reaches about 15 million degrees and the pressure is immense. Under these conditions, hydrogen nuclei are forced close enough together that they can fuse into helium. This process requires overcoming the electromagnetic repulsion between positively charged protons, which is why it only happens at extreme temperatures and pressures. When 4 hydrogen nuclei fuse into 1 helium nucleus, a small amount of mass is converted into energy, according to Einstein's famous equation relating mass and energy. That energy radiates outward through the star, generating the pressure that holds the star up against its own gravity. Our Sun converts roughly 600 million tons of hydrogen into helium every second. That sounds like an enormous rate of consumption, and it is. Yet the Sun contains so much hydrogen that it has been burning at this rate for 4.6 billion years and will continue for roughly another 5 billion years before the hydrogen in its core runs out. The Sun is middle-aged, roughly halfway through its life as a hydrogen-burning star. But what happens when the hydrogen does run out? This is where the story begins to lead toward neutron stars. When a star exhausts the hydrogen in its core, the fusion reactions that have been holding the star up against gravity begin to falter. The core contracts under its own weight, compressing and heating up. This contraction releases gravitational energy, some of which heats the shell of hydrogen just outside the core, triggering fusion in that shell. Meanwhile, the core itself continues to contract until it reaches temperatures high enough to ignite helium fusion. Helium fusion is a different process entirely. 3 helium nuclei combine to form 1 carbon nucleus in what physicists call the triple alpha process. This reaction requires higher temperatures than hydrogen fusion, roughly 100 million degrees compared to 15 million for hydrogen. But once conditions become extreme enough, helium burning begins, and the star has found a new source of fuel. For a star like our Sun, this is essentially the end of the road. The Sun will expand into a red giant as helium fusion proceeds, eventually shedding its outer layers to form a beautiful glowing shell called a planetary nebula. The core will remain as a white dwarf, a dense remnant supported by the quantum pressure of electrons. The white dwarf will slowly cool over billions of years, eventually fading into darkness. But the Sun will never become a neutron star. It is not massive enough. Stars much more massive than the Sun face a different fate. When a star begins its life with more than roughly 8 times the mass of the Sun, it can climb much higher up the nuclear fusion ladder. After helium is exhausted, the core contracts further and heats further until carbon fusion ignites. Carbon combines to form neon, magnesium, and other elements. When carbon is exhausted, the process repeats: contraction, heating, and ignition of the next fusion stage. The sequence continues through progressively heavier elements. Carbon burning produces neon and magnesium. Neon burning produces oxygen and magnesium. Oxygen burning produces silicon and sulfur. Silicon burning produces iron and elements near iron on the periodic table. Each stage requires higher temperatures than the last, and each stage proceeds faster than the last. Consider the timescales involved. A massive star might burn hydrogen in its core for 10 million years. When the core switches to helium burning, that stage lasts perhaps 1 million years. Carbon burning takes only about 1,000 years. Neon burning lasts roughly 1 year. Oxygen burning continues for perhaps a few months. Silicon burning, the final stage, lasts only about a day. The star is racing toward its own death, burning through fuel faster and faster, like someone spending savings more recklessly as the account dwindles. The core grows hotter and denser with each stage. The star has no idea, of course. Stars do not think, but if you could somehow watch the process unfold, you would see a star desperately fighting against gravity, burning through every available fuel source, finding temporary reprieves that grow shorter and shorter. And then the star reaches iron, and everything changes. Iron occupies a unique position in nuclear physics. It sits at the peak of the binding energy curve, meaning that iron nuclei are more tightly bound than any other nuclei. Fusing elements lighter than iron releases energy, which is why fusion can power stars through the sequence from hydrogen to iron. But fusing iron into heavier elements does not release energy. It requires energy. Iron is the ash of stellar fusion, the dead end of the nuclear burning sequence. A massive star in its final days develops an onion-like structure. At the center sits a core of iron, produced by silicon burning. Surrounding this iron core are shells of progressively lighter elements: silicon, oxygen, neon, carbon, helium, and finally hydrogen at the outermost layers. Each shell is the remnant of a previous burning stage, a layer of ash left behind as the fusion moved to heavier and heavier elements. The iron core cannot produce energy through fusion. It can only sit there, growing larger as silicon burning in the surrounding shell adds more iron to it. The core is held up against gravity, not by fusion energy, but by electron degeneracy pressure, the quantum mechanical resistance of electrons to being compressed into too small a space. This is the same pressure that supports white dwarf stars. But there is a limit to what electron degeneracy pressure can support. That limit was calculated in the 1930s by astrophysicist Subrahmanyan Chandrasekhar, who showed that electron degeneracy pressure can only support a mass up to about 1.4 times the mass of the Sun. This is called the Chandrasekhar limit. For white dwarf stars, this limit is never approached during normal stellar evolution. But the iron core of a massive star can exceed this limit. When the iron core grows past the Chandrasekhar limit, disaster strikes. Electron degeneracy pressure is no longer sufficient to hold the core up against gravity. The core begins to collapse. What happens next unfolds so quickly that calling it sudden would be a profound understatement. The core collapse takes less than 1 second. In that brief interval, more happens than in the previous million years of the star's life combined. The collapsing core reaches speeds of roughly 70,000 kilometers per second, about 1/4 the speed of light. A region of space roughly the size of Earth compresses down to an object roughly the size of a city in less than a second. The density skyrockets. The temperature soars into the hundreds of billions of degrees. Nothing like this happens anywhere else in the universe except in the earliest moments after the Big Bang. As the density increases, electrons are forced to combine with protons in a process called electron capture. Protons absorb electrons and transform into neutrons, releasing particles called neutrinos in the process. The neutrinos carry away enormous amounts of energy, more energy in 10 seconds than the Sun will emit in its entire 10 billion-year lifetime. This neutrino burst passes through the outer layers of the star as if they were not there. Neutrinos barely interact with matter. They are almost undetectable, but the energy they carry is real and immense. And the core continues to collapse until it reaches nuclear density, roughly 200 to 400 billion grams per cubic centimeter. At this point, the neutrons begin to resist further compression. Like electrons, neutrons are subject to quantum mechanical pressure arising from the Pauli exclusion principle. Neutrons refuse to occupy the same quantum state. When compressed to nuclear density, this neutron degeneracy pressure becomes enormous. The collapsing core slams into this wall of quantum resistance. The collapse halts, but the outer layers of the core are still falling inward at tremendous speed. They crash into the suddenly rigid inner core and bounce. A shockwave forms, moving outward through the collapsing star. In principle, this shockwave should blow the star apart. In practice, the physics is more complicated. The shockwave loses energy as it travels outward, stalling somewhere in the outer layers of the collapsing core. For a supernova explosion to occur, the shockwave must be revived, re-energized, to continue its outward push. The exact mechanism of this revival remains an active area of research. Neutrino heating appears to play a crucial role. Turbulence and instabilities contribute as well. The details are complex and not fully understood, but the outcome is clear from observations. The shockwave does revive, and it blows the outer layers of the star into space. This is a core collapse supernova. The outer layers of the star, everything except the collapsed core, are blasted outward at speeds of 10,000 kilometers per second or more. The explosion releases an almost incomprehensible amount of energy. For a few weeks, a single supernova can outshine an entire galaxy containing 100 billion stars. Anyone looking at that galaxy during those weeks would see a new point of light, brighter than all the other stars combined. Throughout recorded history, humans have observed several supernovae visible to the naked eye. In 1054 AD, Chinese and Japanese astronomers recorded a guest star that appeared suddenly in the constellation we now call Taurus. It was visible in daylight for 23 days and remained visible at night for nearly 2 years. The debris from that explosion is still visible today as the Crab Nebula, a glowing cloud of gas expanding outward at over 1,000 kilometers per second. At the center of the Crab Nebula sits a neutron star, the collapsed core of the star that exploded nearly 1,000 years ago. In 1572, the Danish astronomer Tycho Brahe observed a supernova in the constellation Cassiopeia, an event that helped challenge the ancient belief that the heavens were unchanging and perfect. In 1604, Johannes Kepler observed another supernova, the last one visible to the naked eye in our own galaxy. Since then, we have had to rely on supernovae in other galaxies, which occur frequently enough that modern astronomers observe dozens per year. The most recent nearby supernova occurred in 1987 in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, about 160,000 light-years from Earth. Supernova 1987A, as it was designated, was the first supernova visible to the naked eye in the era of modern astronomy. For the first time, astronomers could study a supernova with modern instruments. Most remarkably, neutrino detectors on Earth detected a burst of neutrinos arriving a few hours before the visible light, exactly as theoretical models had predicted. Those neutrinos came directly from the collapsing core, passing through the outer layers of the star, while the shockwave was still struggling to break through. After the explosion fades and the ejected material expands into space, what remains at the center depends on the mass of the original star. If the collapsing core weighs less than about 2 to 3 solar masses, it stabilizes as a neutron star, supported by neutron degeneracy pressure against further collapse. If the core is more massive, even neutron degeneracy pressure cannot hold it up. The collapse continues past neutron star density, past any known form of matter, until an event horizon forms and the core becomes a black hole. The dividing line between neutron star and black hole depends on the original mass of the star, but the relationship is not straightforward. Stars lose mass throughout their lives through stellar winds, and more mass is ejected in the supernova explosion itself. Roughly speaking, stars that begin their lives with about 8 to 20 solar masses tend to leave neutron star remnants, while stars more massive than about 20 to 25 solar masses tend to leave black holes. But there is significant uncertainty in these numbers, and the details depend on factors like the star's composition and the specifics of the explosion mechanism. The neutron star exists in a narrow window of possibility. It is massive enough to have crushed atoms out of existence, forcing electrons and protons to merge into neutrons. But it is not quite massive enough to collapse entirely into a black hole. It is balanced on a knife's edge between two forms of oblivion. A little less mass, and it would have become a white dwarf. Atoms intact, electrons still orbiting nuclei. A little more mass, and it would have vanished behind an event horizon, becoming a region of spacetime from which nothing can escape. Instead, it exists as something in between, something that should not be possible, yet clearly is. In that final second of collapse, more happens than in millions of years of the star's prior existence. An entire sun's worth of matter is crushed into a ball you could drive across in 15 minutes. The atomic structure that defines everything in your ordinary experience is erased, replaced by something utterly alien. The object left behind glows with the heat of its violent birth, rotates with speeds that seem to mock the laws of physics, and generates magnetic fields strong enough to reshape the nature of matter itself. The star has died, but something new has been born from its corpse, something stranger than the star ever was. Something that will spin in the darkness for millions or billions of years, a monument to the most extreme physics in the universe, a reminder that nature is far stranger and more wonderful than our everyday experience would ever suggest. Let us take an impossible journey. Let us descend through a neutron star layer by layer, from its thin atmosphere to its mysterious core, exploring conditions so extreme that our language struggles to describe them, and our mathematics strains to calculate them. Some of what we are about to explore is well-established physics, confirmed by decades of observation and calculation. Some is educated guesswork, theoretical models that fit the data but remain unproven, and some remains genuinely unknown, mysteries that the laws of physics have not yet fully revealed to us. Remember the scale of what we are exploring. A neutron star measures roughly 12 to 15 miles across. You could fit one comfortably within the boundaries of a major city. From a distance, it would not look particularly impressive, just a small sphere hanging in space, perhaps glowing faintly with residual heat. But that modest sphere contains more mass than our entire sun, and every mile of our descent will take us into conditions more extreme than the last. We begin at the surface, or rather just above it, in the neutron star's atmosphere. Yes, neutron stars have atmospheres, though calling them thin would be a profound understatement. A neutron star atmosphere measures only millimeters to centimeters thick, a whisper of gas clinging to the surface against gravity that would crush any ordinary material instantly. This atmosphere consists of hydrogen, helium, or carbon depending on the star's history, what materials have fallen onto it over millions of years, whether it has a companion star feeding it matter. The temperature here is staggering. The surface of a neutron star glows at temperatures between 600,000 and over 1 million degrees Celsius. For comparison, the surface of our sun measures about 5,500 degrees. The surface of a neutron star is roughly 100 to 200 times hotter than the surface of the Sun. If you could see a neutron star up close, it would glow with a fierce blue-white light, radiating energy across the electromagnetic spectrum from radio waves to X-rays. But temperature is not the most extreme thing about the surface. Gravity is. The surface gravity of a neutron star is roughly 200 billion times the surface gravity of Earth. On Earth, if you drop a ball, it falls at about 10 meters per second squared. On a neutron star, that same ball would accelerate at about 2 trillion meters per second squared. A marshmallow dropped onto a neutron star surface would impact with the energy of a small nuclear weapon. The kinetic energy of falling just a few feet in such intense gravity would be enough to vaporize any ordinary object. Standing on a neutron star is not merely impossible for practical reasons. It is impossible in principle. If you somehow teleported to the surface of a neutron star, you would not stand. You would not even have time to fall. The gravitational tidal forces, the difference in gravity between your head and your feet, would be so extreme that you would be stretched and compressed simultaneously, pulled apart at the atomic level in a fraction of a nanosecond. Your body would be reduced to a thin film of plasma smeared across the surface, and even that plasma would be compressed into the crust almost instantly. The gravity is so intense that light itself bends noticeably. If you could somehow hover above a neutron star and look at its surface, you would see something strange. You would be able to see more than half the surface at once, because light from the far side of the star bends around toward your eyes. The geometry of space itself is warped by the neutron star's mass. General relativity, Einstein's theory of gravity, predicts this effect, and observations of neutron stars confirm it. Now let us descend through that thin atmosphere and reach the outer crust. Just below the atmosphere lies a solid layer, a crust of crystalline matter, unlike anything on Earth. This crust is composed primarily of iron nuclei arranged in a lattice structure, like the atoms in a metal, but far more tightly packed. The crust extends about 1 to 2 kilometers deep, a relatively thin shell surrounding the denser material beneath. The density at the top of the crust is roughly 1 million grams per cubic centimeter, similar to the density of a white dwarf star. This is already 1 million times denser than water, 1 million times denser than anything you have ever touched. A cubic centimeter of this material, about the size of a sugar cube, would weigh about a ton. But by neutron star standards, this outer crust is practically fluffy. The density increases rapidly as we descend. The outer crust is the strongest material in the universe. It is roughly 10 billion times stronger than steel. Diamond, the hardest natural material on Earth, would crumble like wet sand compared to neutron star crust. This incredible strength comes from the electromagnetic forces between the tightly packed nuclei and the electrons that permeate the lattice. The nuclei are locked into place by forces so powerful that deforming the crust requires enormous energy. This strength has observable consequences. Neutron star crusts can support irregularities, bumps and depressions on the surface. But these mountains, if you can call them that, are measured in millimeters or at most centimeters. A mountain on a neutron star might be a fraction of an inch tall. Anything higher would be crushed flat by the star's own gravity. The surface of a neutron star is smoother than the smoothest surface ever manufactured on Earth, not because it was polished, but because gravity allows nothing else. Sometimes the crust does crack. When stresses build up beyond what even this incredibly strong material can withstand, the crust fractures suddenly. These events are called starquakes, and they release tremendous amounts of energy. A starquake might release as much energy as a significant earthquake on Earth, but concentrated into a region only a few kilometers across. The energy manifests as a sudden change in the neutron star's rotation rate, and often as a burst of radiation detectable across interstellar distances. We will return to starquakes later when we discuss magnetars, where these events reach their most extreme expression. Now we descend deeper, into the inner crust. This region extends from roughly 1 kilometer to perhaps 10 kilometers below the surface. Here, things begin to get truly strange. As density increases with depth, the nuclei in the crust become increasingly neutron-rich. In ordinary matter, Atomic nuclei contain roughly equal numbers of protons and neutrons. A carbon nucleus has 6 protons and 6 neutrons. An iron nucleus has 26 protons and typically 30 neutrons. But in the extreme density of the inner crust, nuclei absorb extra neutrons, becoming isotopes that would be unstable under normal conditions. At a certain depth, the nuclei become so neutron-rich that they cannot hold any more. Neutrons begin to leak out, dripping free of the nuclei and forming a sea of unbound neutrons that permeates the space between the nuclei. Physicists call this phenomenon neutron drip. The inner crust becomes a bizarre mixture of neutron-rich nuclei swimming in a fluid of free neutrons, something that exists nowhere else in the known universe. As we descend still deeper, the nuclei themselves begin to deform. The competition between nuclear forces, which try to pull the nuclei into spherical shapes, and electromagnetic forces, which try to push them apart, creates strange geometries. The nuclei stretch and merge into elongated shapes, rods and sheets, and more complex forms. Physicists have given these structures whimsical names based on their resemblance to Italian food. At certain depths, the nuclei form spherical clusters that physicists call nuclei. Deeper still, the spheres merge into long cylindrical rods called spaghetti. Even deeper, the rods merge into flat sheets called lasagna. The sheets can then develop cylindrical holes called antispaghetti or bucatini, and finally the structure inverts into spherical holes in a sea of nuclear matter called antinocchi or Swiss cheese. This nuclear pasta, as the collection of structures is called, may be the strongest material in the universe. Calculations suggest it is roughly 10 billion times stronger than steel, even stronger than the crystalline outer crust. The pasta layer is incredibly difficult to study because we cannot recreate the conditions in any laboratory on Earth. We can only infer its properties from theoretical models and from subtle effects on neutron star behavior. If you could somehow zoom into this layer with a microscope powerful enough to see individual nuclei, you would see shapes that look nothing like the round nuclei in your high school chemistry textbook. You would see spaghetti strands of nuclear matter stretching for comparatively enormous distances, sheets of protons and neutrons layered like phyllo dough, holes and tunnels and complex geometries that emerge purely from the mathematics of nuclear forces under extreme compression. Nature is making pasta out of protons and neutrons, and the recipe exists nowhere else in the cosmos. Now we pass through the pasta layer and enter the outer core. This region begins roughly 10 kilometers below the surface, and here atomic nuclei cease to exist entirely. The individual nuclei have merged into a continuous fluid of nuclear matter, a sea of neutrons with a small admixture of protons and electrons. The density in the outer core reaches 200 to 400 billion grams per cubic centimeter. A teaspoon of this material would weigh roughly 100 million tons. We are now far beyond anything that exists on Earth or anywhere else except inside neutron stars and in the brief instance of neutron star collisions. The matter here is so dense that it exceeds the density inside atomic nuclei themselves. Particles that would normally be separated by the structure of nuclear physics are now crushed together in a continuous mass. Here we encounter one of the most remarkable phenomena in all of physics. The neutrons in the outer core form a superfluid. A superfluid is a state of matter with exactly zero viscosity. It flows without any friction whatsoever. If you could set a superfluid spinning, it would continue spinning forever, never slowing down, never dissipating energy to heat. This seems to violate common sense, but it is a direct consequence of quantum mechanics applied to matter at extremely low temperatures, or, in this case, extremely high densities. The superfluidity of neutron star matter has observable consequences. When a neutron star rotates, the superfluid interior does not rotate smoothly like an ordinary fluid. Instead, it forms vast numbers of tiny whirlpools called vortices. Each vortex carries a fixed amount of angular momentum determined by quantum mechanics. A neutron star might contain roughly a billion vortices, each one a microscopic thread of rotating superfluid stretching through the interior. These vortices tend to pin to the crust. attaching themselves to irregularities in the solid lattice above. As the crust gradually slows down due to magnetic braking, the vortices remain pinned, and a velocity difference builds up between the crust and the superfluid interior. Eventually, the stress becomes too great, and the vortices suddenly unpin and transfer their angular momentum to the crust. The crust suddenly speeds up, and the neutron star experiences a glitch, a sudden increase in rotation rate. Pulsar glitches have been observed in many neutron stars, providing direct evidence for superfluid interiors. Imagine a liquid so perfect that once set in motion, it would flow forever without slowing down. Imagine that liquid filling a sphere the size of a city, containing more mass than the sun, spinning hundreds of times per second. Imagine that liquid threaded with a billion tiny whirlpools, each one locked in place by quantum mechanical law. That is what fills most of a neutron star's interior, and it is a direct window into quantum physics operating on scales vastly larger than atoms. The protons in the outer core, though only a small fraction of the total, also exhibit quantum behavior. They form a superconductor, a state of matter in which electrical current flows without resistance. In an ordinary metal, electrical resistance converts some energy to heat whenever current flows. In a superconductor, current flows forever without any energy loss. The superconducting protons in a neutron star help generate and maintain the star's magnetic field, creating structures of magnetic flux that thread through the interior. Now we approach the most mysterious region of all, the inner core. This region occupies perhaps the innermost 2 to 3 kilometers of the neutron star. The density here exceeds 500 billion grams per cubic centimeter and may climb higher still toward the center. We have reached conditions so extreme that our physics becomes genuinely uncertain. What happens to matter at these densities? We do not know for certain. Our theories make predictions, but we cannot test them directly. The densities in neutron star cores exceed anything we can create in any laboratory on Earth, even for the briefest instance. We can only theorize and try to match our theories to observations, inferring the properties of matter we can never touch. One possibility is that the inner core is simply more of what we found in the outer core. Neutron superfluid compressed even further, with the same basic physics continuing to higher densities. This would make the neutron star relatively simple in structure, just increasingly dense neutron matter all the way to the center. A second possibility introduces particles called hyperons. Hyperons are relatives of protons and neutrons, containing a type of quark called a strange quark, in addition to the up and down quarks that make up ordinary nuclear matter. Under normal conditions, hyperons are unstable, decaying in a tiny fraction of a second. But at the extreme densities of a neutron star core, hyperons might become stable because there is not enough room for all the neutrons. Creating hyperons provides a way for the matter to reduce its energy by occupying different quantum states. If hyperons appear in neutron star cores, they have significant consequences for the star's structure. Hyperons would make the matter softer, less able to resist compression. This would lower the maximum possible mass for a neutron star. We have observed neutron stars with masses around 2 solar masses, which places constraints on how many hyperons can be present. This is called the hyperon puzzle, the challenge of reconciling the possible existence of hyperons with the observed masses of neutron stars. A third possibility is even more exotic. At the highest densities, the neutrons themselves might dissolve. Neutrons are not fundamental particles. Each neutron is composed of 3 quarks held together by the strong nuclear force. At extreme enough densities, the quarks might break free from their confinement within individual neutrons and form a new state of matter called quark matter. This would be a soup of quarks and gluons, the particles that carry the strong force, all mixed together in a continuous fluid. If quark matter exists in neutron star cores, it would represent the most extreme form of matter possible, short of a black hole. The quarks would be deconfined, freed from the prisons of protons and neutrons that normally contain them. This state of matter existed briefly in the first microseconds after the Big Bang, when the entire universe was hot and dense enough for quarks to roam free. Inside neutron star cores, this primordial state might persist permanently, a relic of the earliest moments of existence preserved by extreme compression. We genuinely do not know which of these possibilities is correct. It is possible that different neutron stars have different interiors, depending on their mass and history. A lower mass neutron star might have a purely neutron core, while a higher mass star might contain hyperons or quark matter. The transitions between different states of matter might occur at specific densities, creating layers within the inner core itself. This uncertainty might seem frustrating, but it is actually one of the most exciting aspects of neutron star physics. The interior of a neutron star represents a frontier of knowledge, a place where our understanding reaches its limits and new physics awaits discovery. Every new observation of neutron star masses, radii, cooling rates, or oscillations provides clues about what lies within. Slowly, piece by piece, we are assembling the puzzle. When physicists at facilities like CERN and Brookhaven National Laboratory smash heavy nuclei together at nearly the speed of light, they create tiny droplets of matter for incredibly brief instants that may resemble what exists inside neutron stars permanently. The quark-gluon plasma, created in these collisions, lasts for only a trillionth of a second before cooling and condensing back into ordinary particles. But neutron star cores maintain these conditions for billions of years. The cosmos has been running this experiment at a scale and duration we can never hope to match. The structure of a neutron star, from its thin atmosphere through its crystalline crust, through the pasta layers and the superfluid ocean and the unknown core, represents a catalogue of physics at the extremes. Each layer challenges our understanding in different ways. Each layer teaches us something about the behavior of matter under conditions we cannot reproduce on Earth. And at the very center, where the density climbs highest and our knowledge fails, the universe keeps secrets we are still learning to read. We have now journeyed from the surface to the center of a neutron star. But our exploration has been static, a snapshot of structure at a single moment. Neutron stars are not static objects. They rotate, often at tremendous speeds. They emit radiation, they pulse, and those pulses gave these objects their first name when humans discovered them: pulsars. Cambridge, England, 1967. A young graduate student named Jocelyn Bell Burnell was working on her doctoral thesis, analyzing data from a new radio telescope she had helped build. The telescope was designed to study quasars, the brilliant cores of distant galaxies powered by supermassive black holes. Quasars had only been discovered a few years earlier, and astronomers were eager to learn more about them. The telescope consisted of over 1,000 wooden posts supporting more than 2,000 dipole antennas spread across 4.5 acres of English countryside. Bell Burnell had spent 2 years helping to construct it, driving posts into the ground and stringing cables in all weathers. Now she was responsible for analyzing the data it produced. Hundreds of feet of chart recorder paper every day, covered with the squiggles of radio signals from across the sky. In August of 1967, Bell Burnell noticed something unusual in the data. Among the expected signals from quasars and the interference from Earth-based sources, there was something strange. She called it scruff at first, a bit of signal that did not quite fit any known category. It appeared at the same position in the sky night after night, which suggested it was truly astronomical rather than terrestrial interference. But it did not look like any known type of radio source. When Bell Burnell examined the scruff more closely using faster chart recorders, she discovered something remarkable. The signal consisted of regular pulses, repeating every 1.337 seconds with extraordinary precision. The pulses were brief, lasting only a small fraction of a second, but they arrived like clockwork, as regular as any signal produced by human technology. The regularity was deeply puzzling. Nothing in nature was known to pulse so precisely. Stars twinkle because of turbulence in Earth's atmosphere, but that produces random fluctuations, not regular pulses. Variable stars change brightness over time, but their periods are measured in days or years, not seconds. Binary stars orbit each other, but again on timescales of hours or days, not fractions of a second. What could possibly tick with such mechanical precision? The first interpretation considered seriously was that the signal might be artificial. Perhaps it was interference from some human-made device, a radar system, or a satellite, or some piece of equipment on the telescope itself. Belle Burnell and her supervisor, Anthony Hewish, checked carefully for terrestrial sources. They found none. The signal came from space. This left another possibility, one that the team discussed half seriously but could not immediately dismiss. Perhaps the signals were coming from an extraterrestrial civilization. Perhaps some intelligence beyond Earth was broadcasting toward us, deliberately or accidentally, and Jocelyn Belle Burnell had stumbled upon the first evidence of alien technology. The team assigned the source a half-joking designation, LGM-1, for Little Green Men. They did not truly believe they had detected aliens, but they could not rule it out. The regularity of the pulses seemed almost too perfect to be natural. What astronomical object could keep time like a clock? The alien hypothesis became much less tenable when Belle Burnell found a second pulsing source in a completely different part of the sky. This new source had a different period, about 1.2 seconds, but the same characteristics, brief pulses repeating with mechanical regularity. If the signals were coming from aliens, it would mean two separate civilizations happened to be broadcasting toward Earth using nearly identical technology. That seemed far less plausible than some unknown natural phenomenon. By the end of 1967, Belle Burnell had found 4 pulsating radio sources. The team published their discovery in February 1968 in the journal Nature, cautiously describing the new objects as pulsating radio sources, without committing to any particular explanation. But theories were already circulating. The answer came from theorist Thomas Gold, who proposed that the pulses came from rapidly rotating neutron stars. Gold's model was elegantly simple. A neutron star born in a supernova explosion would be rotating rapidly due to conservation of angular momentum. The star would have a powerful magnetic field, and charged particles accelerated by this field would emit beams of radio waves from the magnetic poles. If the magnetic poles were not aligned with the rotational poles, these beams would sweep around as the star rotated, like the beams of a lighthouse sweeping across a dark shore. Every time a beam swept past Earth, radio telescopes would detect a pulse. The period of the pulses would equal the rotation period of the star. The incredible regularity of the pulses would reflect the incredible regularity of the rotation, governed by the conservation of angular momentum and the neutron star's enormous moment of inertia. A flywheel the size of a city, weighing more than the sun, would be extraordinarily difficult to speed up or slow down, so the rotation would be remarkably stable. Gold's model made a specific prediction: the pulses should be slowing down. A rotating neutron star loses energy through its magnetic field, and this energy loss should cause the rotation to gradually slow. The slowdown would be tiny, perhaps a few billionths of a second per day, but it should be measurable with sufficiently precise timing. When astronomers looked for this slowdown, they found it, exactly as Gold had predicted. The lighthouse model was confirmed. The lighthouse model explains why we see pulsars at all. A neutron star emits radiation continuously from its magnetic poles, but we only see that radiation if the beam happens to sweep across our line of sight. For every pulsar we detect, there may be many more neutron stars whose beams never cross Earth. They are just as real, just as energetic, but invisible to us because geometry has not placed us in the path of their beams. Think about a lighthouse on a dark coast. The light is always on, rotating steadily, but a sailor only sees it when the beam sweeps past their position. If you stand too far north or south of the beam's sweep, you never see the light at all. You might not know the lighthouse exists. Pulsars work the same way. We see only the ones whose beams happen to illuminate our particular location in the galaxy. The discovery of pulsars earned the 1974 Nobel Prize in Physics, awarded to Anthony Hewish and Martin Ryle for their work in radio astronomy. Jocelyn Belle Burnell, whose careful analysis of the data had actually found the first pulsar, was not included. This omission has been widely criticized in the decades since, and Belle Burnell herself has received numerous other awards and honors. She has been remarkably gracious about the Nobel controversy, noting that students are often not included in such prizes, but many in the scientific community consider her exclusion a significant injustice. Since that first discovery, astronomers have found over 3,400 pulsars. They come in many varieties. Some spin slowly, once every few seconds. Others spin astonishingly fast, hundreds of times per second. Some are isolated, drifting alone through space. Others orbit companion stars, sometimes ordinary stars, sometimes white dwarfs, sometimes other neutron stars. Each variety teaches us something different about these remarkable objects. The fastest pulsars belong to a category called millisecond pulsars. These objects rotate so rapidly that their periods are measured in thousandths of a second. The current record holder is a pulsar designated PSRJ 1748-2446 AD, which spins 716 times per second. To put this in perspective, a point on its equator is moving at roughly 24% the speed of light. Nothing can travel faster than light, and this pulsar's surface is moving at nearly a quarter of that ultimate speed limit. At 716 rotations per second, the pulsar completes one full rotation in about 1.4 milliseconds. In the time it takes you to blink, the pulsar has rotated roughly 250 times. If it were spinning any faster, the centrifugal force at the equator would overcome even the neutron star's immense gravity, and the star would tear itself apart. The fastest pulsars are spinning at very nearly the maximum possible rate. Millisecond pulsars did not start out spinning so fast. They are old pulsars that have been spun up by accretion from a companion star. The companion, typically a normal star that has evolved into a red giant, dumps material onto the neutron star. This material carries angular momentum, which is transferred to the neutron star, increasing its spin rate. Over millions of years, the neutron star can be accelerated from a sedate rotation of once per second to hundreds of rotations per second. Astronomers call these recycled pulsars, old neutron stars given new life and new spin by cannibalizing a companion. The precision of pulsars is extraordinary. Some millisecond pulsars are more stable than atomic clocks, the most precise timekeeping devices humanity has ever built. The arrival times of pulsars can be predicted with accuracies of billionths of a second over periods of years. This precision makes pulsars invaluable for testing fundamental physics. The first great test came from a binary pulsar, a pulsar in orbit around another neutron star. In 1974, Russell Hulse and Joseph Taylor discovered PSR B1913+16, two neutron stars orbiting each other every 7.75 hours. Because pulsars keep such precise time, Hulse and Taylor could measure the orbit with extraordinary accuracy. They found that the orbit was shrinking. The two neutron stars were spiraling toward each other, losing energy somehow. Einstein's general theory of relativity predicted exactly this effect. According to general relativity, accelerating masses emit gravitational waves, ripples in the fabric of spacetime. These waves carry energy away from the system, causing the orbit to shrink. Hulse and Taylor measured the rate of orbital decay and found it matched Einstein's prediction perfectly, to within a fraction of a percent. This was the first indirect evidence for gravitational waves, and it earned Hulse and Taylor the 1993 Nobel Prize in Physics. Pulsars have been used for many other precision tests of general relativity. The Shapiro delay, the extra time light takes when passing through curved spacetime near a massive object, has been measured using pulsars. The precession of orbits, the gradual rotation of the orbital ellipse itself, has been measured in binary pulsars and matches relativistic predictions. General relativity has passed every test pulsars have posed, but astronomers continue to search for deviations that might point to new physics. One of the most ambitious uses of pulsar timing is the search for gravitational waves from supermassive black holes. When two galaxies merge, their central black holes eventually spiral together and coalesce. The gravitational waves from such mergers are too low in frequency to be detected by ground-based detectors like LIGO, but they might be detectable through their effect on pulsar timing. Gravitational waves passing through our region of space would cause tiny variations in the arrival times of pulsar pulses. By monitoring dozens of pulsars across the sky for years or decades, astronomers can search for correlated timing variations that would indicate a gravitational wave background. In 2023, several pulsar timing array projects announced evidence for exactly such a background, likely caused by the combined signal of many merging supermassive black hole pairs throughout the universe. Pulsars are now functioning as a galaxy-sized gravitational wave detector. The precision of pulsars has even been proposed as a navigation system for spacecraft. If a spacecraft carried a small X-ray telescope capable of detecting pulsars, it could determine its position in the solar system by comparing the arrival times of pulsars from different pulsars. This would work anywhere in the solar system without requiring communication with Earth. NASA has tested this concept on the International Space Station, and it may be used for deep space missions in the future. When the Voyager spacecraft were launched in 1977, their golden records included a diagram showing Earth's position relative to 14 pulsars. Each pulsar was identified by its period, encoded in binary. The idea was that any intelligent species finding the spacecraft could use the pulsars to locate where it came from. Pulsars are so unique and so stable that they serve as cosmic addresses, landmarks that any sufficiently advanced civilization would recognize. Beyond radio, pulsars emit radiation across the electromagnetic spectrum. X-ray pulsars are neutron stars in binary systems, accreting matter from a companion star. As material falls toward the neutron star, it is channeled by the magnetic field toward the poles, where it crashes onto the surface and heats to temperatures of millions of degrees. The hotspots emit X-rays, and as the star rotates, these X-rays pulse in and out of view. Gamma-ray pulsars emit the most energetic photons of all. The Fermi Gamma-ray Space Telescope has discovered hundreds of pulsars emitting gamma rays, including some that are invisible at radio wavelengths. These gamma rays come from particles accelerated to extreme energies in the pulsar's magnetosphere, the region of space dominated by its magnetic field. Some pulsars are intermittent, switching on and off unpredictably. Some emit only occasional bursts, rather than continuous trains of pulsars. The variety is enormous, and each type provides a window into different aspects of neutron star physics: the magnetic field geometry, the particle acceleration mechanisms, the interaction with companion stars, the properties of the superfluid interior. All of these leave signatures in the pulsar emission. We have catalogued about 3,400 pulsars in the Milky Way. But this is certainly a tiny fraction of the total population. Estimates suggest that our galaxy contains somewhere between 100 million and 1 billion neutron stars. Most of these are invisible to us, either because their beams do not cross Earth, or because they have cooled too much to detect, or because they spin too slowly to emit detectable pulses. For every pulsar we have found, there may be 100,000 more spinning in the darkness, their beams sweeping across empty space, never crossing any telescope on any planet. New telescopes are finding more pulsars every year. The 500-meter aperture spherical telescope in China, known as FAST, is the largest single-dish radio telescope in the world, and it has discovered hundreds of new pulsars since it began operation. The Mercator Array in South Africa has proven especially skilled at finding pulsars in dense stellar environments. The Square Kilometre Array, currently under construction in Australia and South Africa, will be the most sensitive radio telescope ever built, and it is expected to discover tens of thousands of new pulsars. Each new pulsar adds to our understanding. Some will be ordinary, confirming what we already know. Some will be strange, challenging our theories and pointing toward new physics. Somewhere out there, there may be pulsars in configurations we have never imagined, doing things we have never seen. The discovery of pulsars in 1967 opened a window into neutron star physics. That window remains open, and we are still learning to see what lies beyond. Pulsars are remarkable objects, cosmic lighthouses sweeping the universe with beams of radiation, keeping time with a precision that rivals our best atomic clocks. But some neutron stars are even more extreme. Some have magnetic fields not merely 1 trillion times stronger than Earth's, but 1,000 trillion times stronger. Some occasionally release more energy in a fraction of a second than the sun emits in 100,000 years. These are magnetars, and they are the most magnetic objects in the known universe. Let us explore them next, after you have had a moment to rest. The neutron stars will wait. They have been spinning for millions of years. They are patient. A magnetar is a neutron star that has taken the already extreme and pushed it into the realm of the almost incomprehensible, where an ordinary neutron star has a magnetic field perhaps 100 million to 1 trillion times stronger than Earth's field. A magnetar has a field 1,000 times stronger still. The numbers become so large that they lose meaning without careful translation. So let us take a moment to understand what we are discussing. Earth's magnetic field measures roughly 0.00005 Tesla at the surface. This field is strong enough to align compass needles, to guide migrating birds across continents, to shield us from some of the charged particles streaming from the sun. It is a gentle field, barely noticeable in everyday life, yet essential for navigation and perhaps for life itself. A typical hospital MRI machine generates a magnetic field of about 1.5 to 3 Tesla. This is strong enough that you must remove all metal objects before entering the room. Watches stop working. Credit cards are erased. Loose metal objects become dangerous projectiles. Medical staff are trained to keep anything ferromagnetic far from the scanner because the field will seize it and pull it violently toward the machine. The strongest continuous magnetic field ever produced in a laboratory is about 45 Tesla. Achieving this requires enormous electromagnets cooled to cryogenic temperatures, consuming megawatts of electrical power. The strongest pulsed field, sustained for only tiny fractions of a second, reaches about 2,800 Tesla. These represent the absolute limits of human magnetic technology. A magnetar's magnetic field reaches 1 quadrillion Tesla. 1 quadrillion Tesla. That is roughly 100 trillion times stronger than the strongest field humans have ever created, even for an instant. It is 1,000,000 billion times stronger than Earth's field. The numbers are so vast that they become almost meaningless, like trying to comprehend the national debt by counting pennies. Let us try to make this concrete. A magnetar's magnetic field is so powerful that it would erase every credit card on Earth from a distance of roughly halfway between Earth and the Moon. Every magnetic stripe, every hard drive, every piece of magnetic storage media on the entire planet would be wiped clean from 100,000 miles away. And that is just one of the less dramatic effects. At the surface of a magnetar, the magnetic field fundamentally alters the behavior of matter. Electron orbitals, which are normally roughly spherical, become extremely elongated along the magnetic field lines. Atoms become cigar-shaped, stretched into needles, pointing along the field direction. The chemistry that governs everything in your experience, the way atoms bond and interact, changes completely in such an environment. Molecules that are stable under normal conditions might be unstable near a magnetar. Molecules that cannot exist in laboratories might form readily. Even empty space behaves differently near a magnetar. According to quantum electrodynamics, the theory that describes how light and matter interact, vacuum itself has properties that can be affected by extreme electromagnetic fields. Near a magnetar, empty space becomes birefringent. This means that light passing through the vacuum travels at different speeds depending on its polarization. The vacuum acts like a crystal, bending and splitting light in ways that seem to defy common sense. This effect, called vacuum birefringence, was predicted decades ago, but is extraordinarily difficult to observe. The fields required are far beyond anything achievable in a laboratory. But in 2017, astronomers announced possible evidence for vacuum birefringence in observations of a neutron star using measurements of polarized light from the star's surface. The observation remains somewhat controversial, but if confirmed, it represents a direct verification of one of the strangest predictions of quantum physics, made possible only because magnetars create conditions we could never reproduce on Earth. The magnetic field of a magnetar is so strong that it exerts significant forces on the star's crust. The field lines are anchored in the crust, threading through the solid lattice of nuclear matter. As the magnetic field evolves over time, shifting and reconfiguring, it stresses the crust. The crust is extraordinarily strong, as we discussed earlier, billions of times stronger than steel. But no material is infinitely strong. Eventually, something has to give. When the stress exceeds what even neutron star crust can withstand, the crust cracks, a starquake occurs. The magnetic field suddenly reconfigures into a lower energy state, and the energy difference is released in a catastrophic burst. The most powerful of these events are called giant flares, and they are among the most energetic phenomena in the universe, short of supernovae and gamma-ray bursts. Consider what happened on December 27, 2004. On that date, instruments on spacecraft throughout the solar system registered an overwhelming burst of gamma rays and X-rays. The source was SGR 1806-20, a magnetar located approximately 50,000 light-years from Earth on the far side of our galaxy. In the first 0.2 of a second, this magnetar released more energy than the Sun will emit in 100,000 years. For a brief instant, it became the brightest source of gamma rays ever observed in our galaxy. The burst was so intense that it affected Earth's atmosphere from 50,000 light-years away. The gamma rays ionized the upper atmosphere, disturbing the ionosphere in ways that were measurable by radio equipment on the ground. A magnetar halfway across the galaxy, an object most people have never heard of, reached out across 50,000 light-years of empty space and touched our planet's atmosphere. If SGR 1806-20 had been located much closer to Earth, the consequences would have been severe. At a distance of 10 light-years, roughly the distance to several nearby stars, the same flare might have caused a mass extinction. The gamma rays would have stripped away the ozone layer, exposing the surface to deadly ultraviolet radiation from the Sun. The atmospheric chemistry would have been disrupted, potentially triggering climate changes. Life on Earth has survived many catastrophes over the past 4 billion years, but a nearby magnetar flare might be one disaster too many. Fortunately, there are no known magnetars within a dangerous distance of Earth. The nearest identified magnetar is thousands of light-years away. But magnetars are difficult to detect when they are quiet, and there may be dormant magnetars much closer that we have not yet identified. The galaxy is vast, and our surveys are incomplete. Giant flares from magnetars are rare. Only 3 have been observed in over 50 years of monitoring. One in 1979, one in 1998, and the 2004 event from SGR 1806-20. But smaller bursts are much more common. Some magnetars emit hundreds of bursts over periods of weeks or months, each one releasing as much energy as the Sun produces in an entire year. These bursts come unpredictably, with no clear pattern or warning. The unpredictability makes magnetars challenging to study. You cannot schedule telescope time for an event that might happen at any moment, or might not happen for years. Astronomers rely on monitoring satellites that continuously watch the sky for high-energy transients. When a magnetar bursts, alerts go out to observatories around the world, and telescopes swing toward the source to catch whatever follow-up observations are possible. Magnetars were not recognized as a distinct class of objects until relatively recently. For years, astronomers puzzled over 2 types of unusual neutron stars. Soft gamma repeaters, or SGRs, were sources that occasionally burst in gamma rays, then fell quiet, then burst again. Anomalous X-ray pulsars, or AXPs, were neutron stars that emitted steady X-rays far more luminous than their rotation could explain. These 2 categories seemed unrelated until astronomers realized they were both magnetars, neutron stars with ultra-strong magnetic fields, viewed at different times or from different angles. Today we know of roughly 30 confirmed magnetars, with perhaps another 30 candidates awaiting confirmation. This is a tiny number compared to the thousands of known radio pulsars. Magnetars appear to be rare, perhaps because the conditions required to create them are unusual, or perhaps because the ultra-strong magnetic field decays relatively quickly, and magnetars become ordinary neutron stars within a few thousand years. How does a magnetar form? This remains an area of active research. The leading theory involves the first few seconds after a neutron star's birth. In those critical moments, the newly formed neutron star is incredibly hot and fluid. Convection currents churn through the interior, moving material in complex patterns. If the neutron star is born rotating very rapidly, with a period of just a few milliseconds, these convection currents can act like a dynamo, amplifying any initial magnetic field to magnetar strengths. The dynamo mechanism is the same basic process that generates magnetic fields in planets and ordinary stars. Moving electrically conducting fluid generates and amplifies magnetic fields. But in a newly born neutron star, the densities are so high and the rotation so fast that the dynamo can operate with extraordinary efficiency, building fields 1,000,000 times stronger than in ordinary neutron stars. If this theory is correct, then whether a supernova produces a magnetar or an ordinary neutron star depends on the details of the collapse. A star that collapses with more angular momentum, spinning faster, is more likely to produce a magnetar. The exact conditions required are still being worked out, but the basic picture seems to fit the observations. There may be a connection between magnetars and some of the most powerful explosions in the universe. Some gamma-ray bursts, the most energetic events we observe in the cosmos, may be powered by newly born magnetars. When certain massive stars collapse, they may form rapidly rotating magnetars that launch jets of material at nearly the speed of light. These jets produce the gamma-ray burst we observe from billions of light-years away. The magnetar itself is hidden inside the chaos of the explosion, but its birth may be responsible for the entire spectacle. Magnetars do not stay magnetars forever. The ultra-strong magnetic field decays over time, converting magnetic energy into heat and radiation. The decay timescale is uncertain, but appears to be roughly 10,000 years. After that, the magnetic field has weakened enough that the star no longer exhibits magnetar behavior. It becomes an ordinary neutron star, perhaps eventually detectable as a radio pulsar if its beam happens to cross Earth. This means that the magnetars we observe today were all born relatively recently in cosmic terms. They are young objects, products of supernovae that occurred within the past few thousand to few tens of thousands of years. The magnetars that formed when the galaxy was young have long since faded into ordinary neutron stars, their brief period of magnetic fury a distant memory. We observe magnetars primarily through their X-ray and gamma-ray emission. The strong magnetic field channels particles toward the poles, where they crash onto the surface and produce hotspots glowing in X-rays. During bursts, the reconfiguring magnetic field releases enormous amounts of energy as gamma rays. Between bursts, magnetars glow steadily in X-rays, powered by the gradual decay of their magnetic fields. Some magnetars also emit radio waves, though not in the same way as ordinary pulsars. Magnetar radio emission is sporadic and unpredictable, sometimes present and sometimes absent, sometimes bright and sometimes faint. The mechanisms producing this emission are not fully understood. Magnetars continue to surprise us, behaving in ways that challenge our theoretical models. Magnetars are like sleeping dragons scattered throughout the galaxy. Most of the time they are quiet, slowly cooling, their beams sweeping through empty space, noticed by no one. But occasionally, one awakens. The crust cracks, the magnetic field reconfigures. Energy stored over centuries releases in a fraction of a second. And across thousands of light years, instruments on Earth register the scream of a dying magnetic field, a burst of radiation that briefly outshines everything else in the galaxy. Then the magnetar falls quiet again, the crust heals, the field begins to build new stresses, and somewhere in the darkness, the cycle begins again. These are patient monsters. They have time to wait, and when they finally release their fury, the universe notices. So far we have explored neutron stars as solitary objects, spinning alone in the void, perhaps occasionally flaring, but fundamentally isolated. But nature does not always leave neutron stars alone. Stars often form in pairs or groups, bound together by gravity. When both members of a binary system are massive enough to end their lives as neutron stars, something remarkable can happen. The two neutron stars, each the corpse of a once mighty star, begin a slow spiral dance that ends in one of the most violent events in the universe. The first binary neutron star system was discovered in 1974 by Russell Hulse and Joseph Taylor using the Arecibo radio telescope in Puerto Rico. The system, designated PSRB 1913+16, consists of two neutron stars orbiting each other every 7.75 hours. One of the neutron stars is a pulsar, emitting radio beams that sweep past Earth with each rotation. The other is radio quiet, detectable only through its gravitational influence on its companion. Because pulsars keep such precise time, Hulse and Taylor could measure the orbit with extraordinary accuracy. They tracked the arrival times of pulsars over months and years, watching how the orbital motion affected the pulse timing. What they found was remarkable. The orbit was shrinking. The two neutron stars were getting closer together. This orbital decay was exactly what Einstein's general theory of relativity predicted. According to Einstein, accelerating masses emit gravitational waves, ripples in the fabric of spacetime itself. These waves carry energy away from the system. As energy is lost, the orbit shrinks. The two objects spiral closer together. Hulse and Taylor measured the rate of orbital decay and compared it to Einstein's prediction. The agreement was extraordinary, matching to within a fraction of a percent. This was the first indirect evidence that gravitational waves exist, and it earned Hulse and Taylor the 1993 Nobel Prize in Physics. The binary pulsar had become a laboratory for testing general relativity. But the orbital decay also means something else. The two neutron stars are spiraling together. Eventually, they will collide. For PSRB 1913+16, the merger will occur in roughly 300 million years. That seems like an enormous span of time by human standards, but it is brief on cosmic scales. The universe is nearly 14 billion years old. 300 million years is a mere 2% of cosmic history. Other binary neutron star systems have even shorter merger times. Some will collide within tens of millions of years. And somewhere in the universe, binary neutron star systems are merging right now. The collisions that will produce gravitational waves detectable on Earth are happening constantly, scattered across the cosmos. What happens when two neutron stars finally merge? The process unfolds in stages, each more violent than the last. In the final years before merger, the two neutron stars are already close, orbiting each other every few hours. The gravitational waves they emit are too weak and at too low a frequency to detect with current instruments, but the waves are there, rippling outward through space-time, carrying energy away, drawing the stars ever closer. In the final days, the orbit has shrunk dramatically. The neutron stars complete an orbit every few minutes. Tidal forces begin to distort them, each star's gravity raising bulges on the other. The gravitational wave emission intensifies. If you could somehow hear gravitational waves as sound, you would hear a rising tone, climbing higher and higher as the orbital frequency increases. In the final seconds, the neutron stars are whipping around each other hundreds of times per second. The tidal forces are now enormous, stretching and squeezing the stars with every orbit. Matter begins to tear away from the surfaces, forming a disk around the binary system. The gravitational waves have become a scream, a chirp, rising rapidly in both frequency and amplitude, and then contact. The two neutron stars collide at a significant fraction of the speed of light. The kinetic energy involved is staggering, equivalent to the total energy output of the Sun over billions of years, released in milliseconds. Matter is compressed, heated, thrown outward in all directions. For a brief moment, conditions at the collision site exceed anything since the Big Bang. What remains at the center depends on the total mass. If the combined mass is below a certain threshold, a rapidly spinning neutron star may form, at least temporarily. This hypermassive neutron star is supported against collapse, partly by its extreme rotation, but it is unstable. Within milliseconds to seconds, it will either shed enough mass and angular momentum to become a stable neutron star, or it will collapse into a black hole. If the combined mass exceeds the maximum possible mass for a neutron star, collapse is inevitable. A black hole forms at the center, swallowing most of the merged material. An accretion disk of neutron-rich matter surrounds the newborn black hole. Jets of material may be launched from the poles at nearly the speed of light. Either way, the merger ejects material into space. Some of this material comes from the tidal tails drawn out before the collision. Some is blasted away by the violence of impact itself. Some may be driven by winds from the accretion disk or the jets. This ejected material carries neutrons in enormous abundance, freshly liberated from the merged neutron stars. On August 17, 2017, humanity witnessed a neutron star merger for the first time. The LIGO and Virgo gravitational wave detectors registered the distinctive chirp of two compact objects spiraling together and colliding. The signal, designated GW170817, lasted about 100 seconds, rising from the low frequencies, where LIGO barely hears, to the high frequencies, where the signal finally merged into noise as the objects collided. Analysis of the gravitational wave signal revealed that the merging objects had masses of about 1.4 and 1.1 solar masses, consistent with neutron stars. The merger occurred in a galaxy called NGC 4993, located approximately 130 million light-years from Earth. In cosmic terms, this is relatively nearby. Light from the merger took 130 million years to reach us, meaning the actual collision occurred when dinosaurs still ruled the Earth. But GW170817 was not just a gravitational wave event. Just 1.7 seconds after the gravitational wave signal peaked, NASA's Fermi satellite detected a burst of gamma rays from the same direction. A short gamma ray burst, one of the most energetic phenomena in the universe, coincident with a gravitational wave detection. For the first time, the same cosmic event had been observed in both gravitational waves and electromagnetic radiation. The detection triggered the largest coordinated astronomical observation campaign in history. Within hours, telescopes around the world swung toward NGC 4993, searching for an optical counterpart. They found it, a new point of light in the galaxy that had not been there before. Over the following days and weeks, over 70 observatories studied the aftermath, using telescopes sensitive to every part of the electromagnetic spectrum, from radio waves to gamma rays. What astronomers observed was a kilonova, a phenomenon that had been predicted but never conclusively seen before. The ejected neutron-rich material from the merger was undergoing rapid nuclear reactions, building heavy elements through a process called rapid neutron capture, or the RA process. The RA process had been theorized for decades as the origin of about half the elements heavier than iron. Elements like gold, platinum, and uranium cannot be made in ordinary stars. They require an environment flooded with neutrons, where atomic nuclei can capture neutrons faster than they decay. Neutron star mergers provide exactly this environment. The ejected material is almost pure neutrons at first, but as it expands and cools, those neutrons are captured by seed nuclei, building heavier and heavier elements in a frenzy of nuclear synthesis. The kilonova associated with GW170817 glowed first blue, then red over the following days. The blue glow came from lighter R process elements heated by radioactive decay. The red glow came from heavier elements, including lanthanides, whose complex electron structures make them particularly efficient at emitting red light. By studying the spectrum of the kilonova, astronomers could identify the specific elements being produced. The merger created several Earth masses worth of gold, not several tons, several Earth masses. The amount of gold produced in that single collision exceeds the total amount of gold that humanity has ever mined by a factor of millions. Platinum was produced in similar quantities. So were other precious metals, and radioactive elements like uranium and thorium that power the heat inside rocky planets. Every gold atom in the ring on your finger, in the contacts of your smartphone, in the dental fillings in your mouth, was created in an event like this. Somewhere in the galaxy, billions of years before the sun was born, two neutron stars spiraled together and exploded. The gold they created scattered through space, mixed with the interstellar gas, and eventually became part of the cloud that collapsed to form our solar system. Some of that gold ended up on Earth, was mined from the ground, and now sits in your jewelry or your electronics. You are wearing the debris of cosmic violence. The most romantic metal in human culture, the symbol of wealth and permanence and love, came from the most violent event in the universe. Two city-sized balls of nuclear matter, each containing more mass than the sun, spiraled together over millions of years, collided at a quarter the speed of light, and in the fireball of their destruction, forged the gold that would one day adorn human fingers. The silver in your silverware likely has the same origin. The platinum in catalytic converters. The iodine in your thyroid gland, essential for producing hormones that regulate your metabolism. These elements are too heavy to be made in ordinary stars. They required the R process. They required neutron star mergers. The 2017 observation confirmed what theorists had suspected for years. Neutron star mergers are a primary source, perhaps the primary source of R process elements in the universe. Every time two neutron stars collide, they seed the cosmos with gold and platinum and uranium. Over billions of years, these elements have accumulated, mixing into the interstellar medium, incorporating into new generations of stars and planets. The rate of neutron star mergers in a galaxy like the Milky Way is roughly 1 every 10,000 to 100,000 years. That sounds rare, and it is by human timescales. But the universe is old. Over the 13 billion-year history of our galaxy, there have been perhaps 100,000 neutron star mergers. Each one produced Earth masses of heavy elements. The cumulative total is enormous. Across the observable universe, neutron star mergers are occurring constantly. On any given day, somewhere in the cosmos, two neutron stars are completing their billion-year spiral and colliding in a burst of gravitational waves and heavy elements. The universe is a factory for gold, operating continuously, scattered across 2 trillion galaxies. GW 170817 opened a new era of multi-messenger astronomy. For the first time, we observed a single event using fundamentally different carriers of information, gravitational waves and light. This is like gaining a new sense, like a person who has only heard music suddenly being able to see the orchestra as well. Gravitational waves tell us about the masses and spins and orbital dynamics of the merging objects. Electromagnetic observations tell us about the matter ejected, the elements created, the environment of the merger. Together, they reveal far more than either could alone. Since 2017, LIGO and Virgo have detected more gravitational wave events, though none with such a clear electromagnetic counterpart. Upgrades to the detectors are improving their sensitivity, allowing them to detect mergers from greater distances. Future detectors, like the planned Einstein telescope in Europe and Cosmic Explorer in the United States, will be even more sensitive, capable of detecting neutron star mergers across much of the observable universe. Each detection will add to our understanding. We will learn how often neutron star mergers occur. We will measure the range of masses involved. We will watch kilanovae in detail, learning exactly which elements are produced and in what quantities. We will test general relativity in the strong field regime, where spacetime is most severely curved. We will probe the equation of state of neutron star matter through the tidal deformations observed in the final orbits. The collision of neutron stars is where many threads of physics come together. General relativity governs the inspiral and the gravitational waves. Nuclear physics determines what happens to the ejected matter. Particle physics may play a role in the moments of highest density. Atomic physics shapes the spectrum of the kilonova as heavy elements form and decay. Astronomy provides the observations that test all these theories. And from this violent intersection of physical laws comes something remarkably relevant to human life. The elements in our bodies, the metals in our technology, the radioactive isotopes that heat planetary interiors. We are connected to neutron star mergers, not just intellectually, but materially. The cosmos forged parts of us in events we can now observe and understand. After the collision settles, after the kilonova fades, what remains is either a black hole or possibly a neutron star, surrounded by the expanding cloud of newly synthesized elements. The sight of such violence becomes, over millions of years, just another patch of space, indistinguishable from its surroundings. But the gold and platinum and uranium travel outward, mixing into the galaxy, eventually finding their way into new stars and new planets. Somewhere, billions of years from now, on a planet we will never know, a creature may look at a piece of yellow metal and wonder where it came from. If they are lucky, if their science has progressed far enough, they may learn the answer. Their gold, like ours, was forged in fire and violence, in the collision of the corpses of dead stars, in an event so powerful that it shook the fabric of spacetime itself. We have spoken of neutron stars as objects balanced on a knife's edge, and now it is time to examine that edge directly. A neutron star exists in a precarious equilibrium between two forms of oblivion. If it was slightly less massive, it would be a white dwarf, a dense stellar remnant, but one where atoms still exist, where electrons still orbit nuclei in recognizable configurations. If it was slightly more massive, it would be a black hole, a region of spacetime so warped that nothing, not even light, can escape. The neutron star occupies the narrow ground between these two fates, and understanding this boundary tells us something profound about the nature of matter itself. The question seems simple enough. How massive can a neutron star be before it collapses into a black hole? But answering this question has proven extraordinarily difficult, and the answer remains uncertain even after decades of research. The challenge is that the maximum mass depends on what neutron stars are made of, and we do not fully understand the properties of matter at neutron star densities. In the 1930s, physicists Tolman, Oppenheimer, and Volkoff worked out the basic theory. They showed that there must be an upper limit to the mass of a neutron star, just as Chandrasekhar had shown there was an upper limit to the mass of a white dwarf. Beyond a certain mass, the pressure generated by neutron degeneracy and nuclear forces cannot resist gravity. The star must collapse. This maximum mass is called the Tolman-Oppenheimer-Volkoff limit, or simply the TOV limit. But calculating the actual value of the TOV limit requires knowing how pressure depends on density inside a neutron star. This relationship is called the equation of state. For ordinary materials, the equation of state is well understood. We know how gases, liquids, and solids respond to compression. We can measure these properties in laboratories and derive them from fundamental physics. But for neutron star matter, compressed to densities hundreds of billions of times greater than anything on Earth, we are extrapolating far beyond any direct experimental knowledge. Different assumptions about the equation of state lead to different predictions for the maximum mass. A stiff equation of state, where pressure increases rapidly with density, can support more mass against gravity. A soft equation of state, where pressure increases more slowly, supports less mass before collapsing. The difference between these extremes is significant. Soft equations of state might predict maximum masses as low as 1.5 solar masses. Stiff equations of state might allow masses up to 2.5 or even 3 solar masses. This uncertainty is not merely academic. It connects to fundamental questions in physics. The equation of state of neutron star matter depends on the behavior of the strong nuclear force at high densities. It depends on whether exotic particles, like hyperons, appear in the core. It depends on whether quarks become deconfined, escaping from their prisons inside neutrons and protons. Getting the equation of state right means understanding quantum chromodynamics, the theory of quarks and gluons, in regimes that are extraordinarily difficult to calculate. Fortunately, nature provides constraints. By measuring the masses of actual neutron stars, we can rule out equations of state that would predict collapse at those masses. If we observe a neutron star with a mass of 2 solar masses, then any equation of state that predicts collapse below 2 solar masses must be wrong. The existence of that star rules it out. Over the past 2 decades, astronomers have found several neutron stars with precisely measured masses near or above 2 solar masses. The pulsar PSR J0740 plus 6620 has a mass of approximately 2.08 solar masses, one of the highest confirmed. These observations rule out the softest equations of state. Whatever neutron star matter is made of, it must be stiff enough to support at least this much mass. But the upper end remains uncertain. We have not found any neutron stars convincingly above 2.3 or 2.4 solar masses. This might mean the TOV limit lies in this range, or it might mean we simply have not found the most massive neutron stars yet. The absence of evidence is not evidence of absence. There is another way to constrain the equation of state. When two neutron stars spiral together before merging, they raise tidal bulges on each other, just as the moon raises tides on Earth. These tidal effects depend on how easily the neutron star material deforms. A star with a stiff equation of state is more resistant to deformation. A star with a soft equation of state squishes more readily. The tidal deformation affects the gravitational wave signal. By analyzing the gravitational waves from neutron star mergers, physicists can measure the tidal deformability and constrain the equation of state. The merger GW170817 provided such a measurement, ruling out the very stiffest equations of state. Combined with the mass measurements that rule out the softest equations, we are narrowing in on the truth. The equation of state lies somewhere in the middle, neither extremely soft nor extremely stiff. The current best estimates place the TOV limit somewhere between 2.0 and 2.5 solar masses. This is still a wide range, but it is much narrower than what we knew 20 years ago. Future observations, including more gravitational wave detections and more precise mass measurements from pulsar timing, will continue to tighten the constraints. What happens when a neutron star approaches this limit? Imagine a neutron star in a binary system, slowly accreting matter from a companion. Gas flows from the companion, spirals down onto the neutron star, and adds to its mass gram by gram, kilogram by kilogram. Over millions of years, the mass creeps upward. At some point, the neutron star crosses the TOV limit. What happens next? There is no explosion. There is no warning. The neutron star simply collapses. The neutron degeneracy pressure and nuclear forces that have been holding it up suddenly become insufficient. The star falls inward, accelerating under its own gravity. In a fraction of a second, the entire mass crosses its own event horizon and becomes a black hole. From outside, you might see a flash of neutrinos, particles that escape from the collapsing matter in the final moments before the event horizon forms. You might detect a burst of gravitational waves as the space-time geometry reconfigures itself, but the electromagnetic signature would be minimal. Unlike a supernova, there is no explosive ejection of matter. The star just disappears. Picture watching a neutron star on this threshold. For millions of years it has existed as the densest stable matter in the universe, rotating steadily, perhaps pulsing in radio waves if its beam crosses your detector. Then, silently, the critical gram arrives. The balance tips. Where there was matter, now there is nothing but a hole in space-time. The pulsar signal, if there was one, simply stops. The object that had been among the most extreme forms of matter has become something else entirely, something that is not matter at all in the conventional sense. Between the heaviest neutron stars and the lightest black holes, there was long thought to be a gap. Observations showed neutron stars up to about 2 solar masses and black holes starting at about 5 solar masses. The region between seemed empty. This mass gap, as astronomers called it, was puzzling. Why should nature avoid creating compact objects in this range? Several explanations were proposed. Perhaps the supernova mechanism somehow prevented the formation of objects in this mass range. Perhaps we were missing them due to observational biases. Perhaps the gap was real and reflected something fundamental about how massive stars die. Recent observations have begun to fill in this gap. Some gravitational wave detections involve objects with masses in the ambiguous range between 2.5 and 5 solar masses. The event GW190814, detected in 2019, involved the merger of a 23 solar mass black hole with a 2.6 solar mass compact object. That smaller object might be the heaviest neutron star ever detected, or it might be the lightest black hole. We cannot tell from the gravitational waves alone, If it was a neutron star, it would push the TOV limit higher than most equations of state predict. If it was a black hole, it would be remarkably light for a stellar mass black hole. Either interpretation is interesting. Either tells us something new about the extremes of stellar evolution. Between neutron stars and black holes, there might be yet another possibility, one even more exotic. If the matter at the center of a neutron star transitions to quark matter, and if strange quarks become abundant, it is possible that an entirely different type of object could form. This hypothetical object is called a strange star. A strange star would be composed entirely of strange quark matter, a mixture of up, down, and strange quarks, all in equal proportions. According to some theoretical models, strange quark matter might actually be more stable than ordinary nuclear matter. If this is true, then strange stars could exist, and they might be difficult to distinguish from ordinary neutron stars through most observations. The strange star hypothesis remains speculative. We have no confirmed detection of a strange star, but the possibility illustrates how much uncertainty remains about the densest matter in the universe. We are not even certain what particles compose the cores of neutron stars, let alone how those particles behave at extreme compression. The boundary between neutron star and black hole is where our understanding of matter reaches its limit. On one side, matter exists in the most compressed form possible while still being matter. On the other side, matter has ceased to exist in any recognizable sense, replaced by pure spacetime geometry. The neutron star is the last stand of matter against gravity's ultimate victory. When we study this boundary, we are really studying the limits of reality itself. How compressed can matter become? What happens to particles at densities that make atomic nuclei seem sparse? What new states of matter might appear when quarks and gluons are squeezed together with forces that dwarf anything achievable in laboratories? These are not just astronomical questions, they are questions about the fundamental nature of the physical world. Every heavy neutron star we discover, every merger we observe, every theoretical constraint we derive brings us closer to answers. We are mapping the edge of the possible, charting the frontier where matter gives way to something else. The neutron star stands at this frontier like a monument, a reminder that the universe contains conditions far stranger than our everyday experience would suggest, and that even the most extreme forms of matter can be understood through careful observation and mathematical reasoning. We have journeyed through the birth of neutron stars, descended through their impossible layers, watched their beams sweep across the cosmos, witnessed their magnetic fury, and seen them collide in cataclysms that forge gold. But why should any of this matter? These objects are thousands of light years away. They will never affect your daily life in any direct way. You will never touch a neutron star, never see one except as data on a computer screen, never feel the gravity or magnetic field of one of these distant objects. Yet neutron stars matter profoundly, not just to astronomers, but to anyone who wants to understand the universe and our place in it. They are laboratories for physics we cannot perform on Earth. They are forges that created atoms in your body. They are tests for our deepest theories about reality. Let us explore why these distant objects are relevant to the quest for knowledge. Consider first what neutron stars teach us about gravity. Einstein's general theory of relativity is our best theory of gravity. It has passed every test we have devised, from the precession of Mercury's orbit, to the bending of light around the sun, to the time dilation measured by atomic clocks on satellites. But all these tests occur in relatively weak gravitational fields. The curvature of spacetime near Earth, or even near the Sun, is gentle compared to what general relativity predicts is possible. Neutron stars provide access to strong gravitational fields. Near a neutron star, spacetime is curved so severely that light bends through noticeable angles. Clocks run measurably slower. The relationship between mass and radius is governed by equations that differ significantly from Newtonian physics. By studying neutron stars, we test general relativity in regimes far beyond anything accessible in the solar system. The binary pulsar observations have been particularly powerful. By timing pulsars in orbit around other compact objects, astronomers can measure relativistic effects with extraordinary precision. The Shapiro delay, The extra time light takes when passing through curved spacetime has been confirmed. The gravitational redshift of pulses climbing out of the pulsar's gravitational well matches predictions. The orbital decay due to gravitational wave emission agrees with Einstein's equations to within a fraction of a percent. General relativity has passed all these tests, but that does not mean we should stop testing. Physics is littered with theories that worked perfectly until they were tested in new regimes. Newton's gravity worked flawlessly for centuries, until measurements became precise enough and conditions became extreme enough to reveal its failures. General relativity might similarly break down under conditions more extreme than we have yet probed. Neutron stars offer the best opportunity to search for such breakdowns. If general relativity needs modification at strong field strengths, neutron stars are where we might first detect deviations. Every new pulsar timing measurement, every gravitational wave detection, every constraint on neutron star structure is another test. So far, Einstein keeps passing, but the search continues. Neutron stars are equally important for testing quantum chromodynamics, the theory of the strong nuclear force. QCD describes how quarks and gluons interact to form protons, neutrons, and atomic nuclei. It is a remarkably successful theory, explaining a vast range of particle physics experiments. But at high densities, QCD becomes extraordinarily difficult to calculate. The difficulty is technical but profound. QCD calculations require summing over vast numbers of possible configurations of quarks and gluons. At the energies and densities of particle accelerators, clever mathematical techniques allow physicists to make predictions that match experiments beautifully. But at the densities inside neutron stars, these techniques break down. We must resort to approximations and numerical simulations that may or may not capture the true physics. Neutron stars provide the only natural laboratory for testing QCD at high density. By measuring neutron star masses and radii, we constrain the equation of state, which in turn constrains QCD. If we can determine that neutron stars contain quark matter, we learn something profound about how quarks behave when compressed together without the usual boundaries of protons and neutrons. The interior of a neutron star is a QCD experiment that nature has been running for billions of years. Particle physicists have their own experiments that touch on similar physics. At facilities like CERN and Brookhaven National Laboratory, heavy nuclei are accelerated to nearly the speed of light and smashed together. For incredibly brief instants, tiny droplets of matter are created at densities and temperatures similar to what exists inside neutron stars. These droplets last for trillionths of a second before flying apart, but during their brief existence, they provide glimpses of the same physics. The connection between accelerator experiments and neutron star observations is a beautiful example of how different branches of physics inform each other. Particle physicists analyze their collisions and make predictions about the equation of state. Astronomers measure neutron star properties and constrain the equation of state. When the constraints agree, we gain confidence that we understand the physics. When they disagree, we learn that something is missing from our theories. Beyond testing fundamental physics, neutron stars teach us about nuclear physics in regimes far beyond anything achievable on Earth. The nuclei inside atoms contain roughly equal numbers of protons and neutrons. In neutron star matter, the ratio is completely different. Neutrons dominate overwhelmingly. How does nuclear physics behave when deprived of almost all protons? This question connects to the symmetry energy, a fundamental quantity in nuclear physics that describes how the energy of nuclear matter changes as the ratio of neutrons to protons varies. Laboratory experiments can measure the symmetry energy near the balanced ratio found in normal nuclei, but extrapolating to the pure neutron matter inside neutron stars requires theoretical understanding that neutron star observations can test. Similarly, neutron stars probe the importance of three-body nuclear forces, interactions that involve three nucleons simultaneously. In ordinary nuclei, three-body forces are a small correction to the dominant two-body forces. But at neutron star densities, the particles are so close together that three-body effects become much more important. Our understanding of three-body forces is incomplete, and neutron stars provide constraints that help complete the picture. Gravitational wave astronomy has opened an entirely new way to study neutron stars. When LIGO detected the neutron star merger GW170817, it was not just an astronomical achievement, it was a triumph of physics across multiple domains. General relativity predicted the gravitational wave signal. Nuclear physics predicted the subsequent kilonova. Particle physics contributed to understanding the dense matter involved. Atomic physics explained the spectrum of the glowing ejector. The gravitational waves from neutron star mergers encode information about the tidal deformability of the stars, which depends on the equation of state. By detecting many mergers and measuring the tidal effects, we can constrain the equation of state from gravitational wave data alone. This is a completely independent approach from measuring masses and radii with electromagnetic observations, providing a powerful cross-check. Future gravitational wave detectors will be far more sensitive than current ones. The planned Einstein telescope in Europe and Cosmic Explorer in the United States will detect neutron star mergers from much greater distances, building catalogs of thousands of events. Each detection will add to our statistical understanding. We will learn the distribution of neutron star masses, the range of equations of state consistent with observations, the rate of mergers in different types of galaxies. In space, the proposed LISA mission will detect gravitational waves at lower frequencies than ground-based detectors. LISA will observe the early stages of neutron star in spirals, millions of years before the final merger. It will watch binary neutron stars slowly spiraling together, testing general relativity over long timescales. The combination of ground-based and space-based detectors will provide a complete picture of neutron star binaries throughout their lives. Neutron stars also connect to our origins in a very direct way. The R process elements synthesized in neutron star mergers include many that are important for life. Iodine, essential for thyroid function, is an R process element. Selenium, an antioxidant that protects cells from damage, is an R process element. These elements could not have been made in ordinary stars. They required the neutron-rich conditions of a neutron star merger or similar event. When you take a vitamin supplement containing selenium, you are swallowing atoms that were created when two neutron stars collided somewhere in the galaxy billions of years ago. When a doctor checks your thyroid hormone levels, they are measuring molecules containing iodine forged in cosmic violence. The connection between neutron stars and human biology is not metaphorical, it is chemical. More broadly, the heavy elements produced in neutron star mergers shape the possibilities for planets and life throughout the galaxy. Rocky planets require elements heavier than hydrogen and helium. The diversity of chemistry that makes complex molecules possible requires a well-stocked periodic table. Without neutron star mergers seeding the cosmos with heavy elements, the universe would be a simpler and perhaps more sterile place. We exist because neutron stars exist, not in some abstract philosophical sense, but in a concrete physical sense. The atoms in our bodies were assembled from elements produced in multiple generations of stellar nucleosynthesis, including the R process contributions from neutron star mergers. We are made of star stuff, and some of that stuff required the most extreme conditions in the universe to form. This connection extends beyond humans. Any life anywhere in the universe that uses chemistry similar to ours would depend on elements forged in extreme events. Neutron star mergers may be essential not just to our existence, but to the existence of life throughout the cosmos. When we study neutron stars, we are studying a process that makes life possible. Finally, neutron stars matter because they expand our understanding of what is possible. Before their discovery, no one knew that matter could be compressed to nuclear densities and remain stable. No one knew that objects could spin hundreds of times per second without flying apart. No one knew that magnetic fields could reach quadrillions of Tesla. Neutron stars expanded our conception of the universe, showing us that reality contains possibilities far stranger than everyday experience suggests. This expansion of imagination has value beyond practical application. Understanding that the universe contains such wonders enriches our conception of existence. It reminds us that our intuitions, evolved for survival on a moderate-sized planet with gentle gravity and weak magnetic fields, capture only a tiny slice of what is possible. The universe is larger and stranger and more wonderful than we would ever have guessed without the guidance of observation and theory. When you look at the night sky, you see points of light, stars burning steadily as they have for billions of years. Hidden among those stars, invisible to your eyes, are neutron stars. Some are pulsing, sweeping beams of radio waves across the galaxy. Some are magnetars, quietly waiting to unleash flares of unimaginable power. Some are spiraling toward companions, destined to merge in cataclysms that will forge gold and shake spacetime. Some are simply cooling, slowly fading, their dramatic births long past. They are out there, right now. They do not care whether you know about them. They do not need human attention to exist. But we can know about them. We can study them across thousands of light years using telescopes and mathematics and careful reasoning. We can understand what they are made of, how they behave, what they tell us about physics, and that understanding connects us to the universe in ways that simple survival never could. We have explored what we know about neutron stars, and it is considerable. We understand how they form in the violent deaths of massive stars. We have mapped their structure from atmosphere to core, at least in broad strokes. We have catalogued their varieties, from radio pulsars to magnetars to the components of merging binaries. We have witnessed their collisions and traced the elements they forge. We have used them to test our deepest theories about gravity and matter. But science is defined as much by what it does not know as by what it does. The history of neutron star research is a history of surprises, of observations that defied expectations, of phenomena that forced theorists to revise their models. And despite more than 50 years of intensive study, neutron stars continue to guard secrets. Let us explore the mysteries that remain, the questions that keep astronomers awake at night, the puzzles that the next generation of scientists will work to solve. The equation of state remains the central unsolved problem. We have discussed it before, but its importance bears repeating. The equation of state describes how pressure relates to density inside a neutron star. It determines the maximum mass, the relationship between mass and radius, the internal composition, the behavior during mergers. Get the equation of state right, and you understand neutron stars. Get it wrong, and everything else is built on sand. Despite decades of work, the equation of state remains uncertain. We have constrained it from both ends. Mass measurements of heavy neutron stars rule out the softest possibilities. Tidal deformability measurements from gravitational waves rule out the stiffest, but a wide range of equations of state remain consistent with all observations. Different models within this range make different predictions about what happens at the highest densities. Does the core contain only neutrons with a small admixture of protons and electrons? Do hyperons appear, strange particles that would soften the equation of state and lower the maximum mass? Does a phase transition occur, with neutrons dissolving into their constituent quarks? Is there a sharp boundary between phases or a gradual crossover? These questions remain unanswered. The uncertainty is not merely a gap in astronomical knowledge. It reflects limitations in our understanding of quantum chromodynamics at high density. QCD is notoriously difficult to calculate when particles are closely packed. The standard techniques that work brilliantly for particle collider experiments become intractable. Lattice QCD, the numerical approach that has solved many problems in particle physics, struggles with the conditions inside neutron stars. Theorists are developing new methods, but progress is slow. Future observations will help. More precise mass measurements, especially of heavy neutron stars, will tighten the constraints from above. Better radius measurements from X-ray observations will narrow the allowed range. More gravitational wave detections of neutron star mergers will provide additional tidal deformability measurements. The NASA mission on the International Space Station has already provided valuable radius constraints, and future missions will do better still. But observations alone may not be enough. Ultimately, we need theoretical breakthroughs, new ways to calculate QCD at high density that can make definitive predictions. The equation of state problem sits at the intersection of astronomy and fundamental physics. Solving it will require advances in both. Pulsar glitches present another enduring puzzle. We have mentioned glitches before, the sudden speed-ups in rotation that some pulsars exhibit. The basic explanation involves the superfluid interior. Vortices in the neutron superfluid become pinned to the crust. As the crust slows down due to magnetic braking, a velocity difference builds up between crust and superfluid. Eventually, the vortices unpin catastrophically, transferring angular momentum to the crust and causing a sudden spin-up. This picture explains the general phenomenon, but the details often do not match. Some glitches are larger than models predict. The recovery after a glitch, the way the pulsar gradually returns toward its pre-glitch behavior, varies in ways that are not fully understood. Some pulsars glitch frequently, others rarely, and we do not entirely understand why. The Vela pulsar is the most famous glitcher, having experienced dozens of large glitches since its discovery. Each glitch provides data about the interior, about how much of the star participates in the event, about how the superfluid couples to the crust. But fitting all the observations into a coherent theoretical picture has proven challenging. The interior of a neutron star is not directly accessible. We can only infer its properties from external behavior, and that inference involves many assumptions. Between glitches, pulsars exhibit timing noise, irregular variations in their rotation that cannot be explained by simple slowdown. This noise might arise from turbulence in the superfluid, from small-scale unpinning events, from changes in the magnetosphere, or from other processes entirely. Understanding timing noise would tell us something about the dynamics of neutron star interiors, but current models are incomplete. Magnetar behavior poses its own set of mysteries. We understand the basic picture. Ultra-strong magnetic fields stress the crust until it cracks, releasing bursts of energy. But the details remain murky. What exactly triggers a giant flare? How does energy build up in the magnetic field before release? Why do some magnetars burst frequently, while others remain quiet for years? The formation of magnetars is particularly puzzling. The leading theory involves rapid rotation and dynamo action in the first seconds after birth. But this raises questions. Why do some supernovae produce magnetars while most do not? What determines whether a collapsing star will spin fast enough? Are there other paths to magnetar formation, perhaps involving binary interactions or unusual supernova physics? Observations of magnetars in supernova remnants can constrain their ages, helping us understand the decay of the magnetic field. But we have only a few dozen magnetars to study, far fewer than ordinary pulsars. Statistics are limited. Each magnetar is in some ways unique, making it difficult to draw general conclusions. The connection between magnetars and other energetic phenomena remains uncertain. Some astronomers have proposed that magnetar bursts power certain types of gamma-ray bursts, the most energetic explosions in the universe. The evidence is suggestive, but not conclusive. Fast radio bursts, mysterious millisecond flashes of radio waves from distant galaxies, were long unexplained until one was traced to a magnetar in our own galaxy. But not all fast radio bursts seem to come from magnetars, and the emission mechanism is not fully understood. Fast radio bursts themselves are one of the newest mysteries in astronomy. First discovered in 2007, these bursts last only milliseconds, but release enormous amounts of energy. They come from distant galaxies, often billions of light years away. Some repeat irregularly. Others have been seen only once. The leading models involve neutron stars of various types, magnetars especially, but alternative explanations have not been ruled out. The 2020 detection of a fast radio burst from the galactic magnetar SGR 1935 plus 2154 was a breakthrough. It demonstrated that at least some fast radio bursts come from magnetars. But the burst from SGR 1935 plus 2154 was much weaker than the extragalactic bursts, raising questions about whether they are truly the same phenomenon at different distances, or whether multiple mechanisms can produce similar signals. The pulsar census presents its own mysteries. We have found about 3,400 pulsars in the Milky Way, but models suggest there should be 100 million to a billion neutron stars in our galaxy. The discrepancy is partly explained by selection effects. We only detect pulsars whose beams cross Earth, and we only detect them if they are bright enough and close enough. But even accounting for these effects, the number of detected pulsars seems lower than expected. The galactic center is particularly puzzling. The dense environment near the supermassive black hole should contain many pulsars. Massive stars, which become neutron stars when they die, are abundant there. Yet we have found remarkably few pulsars near the galactic center. The interstellar medium in that direction is dense, scattering radio waves and making pulsars harder to detect. But even accounting for this, the deficit seems real. Are there pulsars there that we simply cannot see? Have the intense conditions somehow destroyed them? Is there something about star formation or stellar evolution near the black hole that prevents neutron star formation? Some supernova remnants, the expanding shells of debris from stellar explosions, lack any detectable neutron star. In some cases, the neutron star might have been kicked away at high speed by asymmetries in the explosion. In some cases, the explosion might have produced a black hole instead, but in some cases, the absence is genuinely mysterious. Where did the compact object go? The variety of neutron star phenomena continues to expand. Rotating radio transients, or RRATs, are neutron stars that emit only occasional pulses rather than continuous trains. They might be ordinary pulsars viewed at an unlucky angle, or they might represent a different emission mode entirely. Central compact objects in supernova remnants are thermally emitting neutron stars that lack the pulsations and strong magnetic fields of ordinary pulsars. Their place in the neutron star zoo is not entirely clear. X-ray dim isolated neutron stars, sometimes called the Magnificent Seven, are nearby neutron stars detected through their thermal X-ray emission. They are relatively old, not associated with supernova remnants, cooling quietly in the solar neighborhood. Their properties do not quite fit any standard category. They rotate slowly, have moderate magnetic fields, and seem to be ordinary neutron stars that have simply aged, but the details of their cooling and emission are not fully explained by models. The question of strange quark matter lingers. If strange quark matter is the true ground state of matter, more stable than ordinary nuclear matter, then strange stars might exist. These would be neutron stars that have converted entirely to strange quark matter, possibly with very different observable properties. Distinguishing a strange star from an ordinary neutron star would be difficult, but not impossible. Certain features of the surface emission, the cooling rate, or the behavior during mergers might differ. No convincing evidence for strange stars has been found, but the hypothesis has not been definitively ruled out either. The idea that all of nuclear physics might be metastable, that given enough time or enough compression, ordinary matter would convert to strange matter, is radical, but radical ideas sometimes turn out to be correct. The universe is not obligated to match our expectations. Neutron star cooling provides another window into the interior, and another set of puzzles. Newly formed neutron stars are incredibly hot, with interior temperatures exceeding 100 billion degrees. They cool rapidly at first, primarily through neutrino emission from the core. The neutrinos pass through the star and escape into space, carrying energy away far more efficiently than photons from the surface. The rate of neutrino cooling depends on the interior composition. If the core contains only neutrons with some protons and electrons, cooling proceeds at a certain rate. If exotic particles like hyperons or quarks are present, different neutrino emission processes become possible, potentially accelerating the cooling dramatically. By measuring the temperatures of neutron stars of known ages, astronomers can constrain what is happening inside. The observations show variety. Some neutron stars seem to cool faster than standard models predict. Others cool more slowly. This variety might reflect differences in mass, which would lead to different central densities and compositions. It might reflect differences in magnetic field strength, which affects heat transport. It might reflect phenomena we have not yet imagined. The Cassiopeia, A neutron star, located in the remnant of a supernova that exploded about 340 years ago, has been studied intensively. Its surface temperature has been observed to decrease over a period of years, the first direct observation of neutron star cooling in real time. The cooling rate is consistent with some models, but not others, providing constraints on the interior physics, but the interpretation remains debated. There are also questions about neutron star atmospheres and surfaces. The thin atmospheres we discussed earlier are difficult to model because the conditions are so extreme. The composition affects the spectrum of emitted radiation, which in turn affects our ability to measure surface temperatures and infer interior properties. If we get the atmospheric model wrong, we get the temperature wrong, and our constraints on the interior become unreliable. The crust might have more complex structure than simple models suggest. Magnetic fields, which thread through the star at different strengths and orientations, could create hotspots and temperature variations across the surface. Buried magnetic fields in the crust could affect heat transport. The interaction between the magnetic field, the temperature distribution, and the emission we observe is complex and not fully understood. Beyond specific puzzles, there is a general sense among researchers that neutron stars still have surprises in store. Every time observational capabilities have improved, new phenomena have been discovered. When radio telescopes became sensitive enough, pulsars appeared. When X-ray satellites launched, X-ray pulsars and magnetars emerged. When gravitational wave detectors began operating, neutron star mergers became directly observable. Future telescopes will push further. The square-kilometer array will be the most sensitive radio telescope ever built, capable of detecting pulsars throughout the galaxy and perhaps in nearby galaxies. The Athena X-ray Observatory, planned for the 2030s, will study neutron stars with unprecedented spectral resolution. Improved gravitational wave detectors will detect mergers from across the universe. What will these instruments find? No one knows for certain. That is the nature of science. We build better tools and point them at the universe, and the universe reveals things we did not expect. The history of neutron star research suggests that the surprises are not over. Somewhere in the data we will collect over the coming decades, there are discoveries waiting to be made, phenomena we have not imagined, behaviors that will force us to revise our understanding. The mysteries that remain are not failures of science, they are opportunities. Each unsolved puzzle is an invitation to learn something new about the universe. Each unexplained observation is a hint that our current theories are incomplete. Science progresses not by confirming what we already know, but by confronting what we do not understand. Neutron stars, for all we have learned about them, remain a frontier. We have traveled far together through this exploration of neutron stars. We have witnessed the deaths of massive stars and the violent births of their collapsed cores. We have descended through layers of matter more compressed than anything on Earth, through crystalline crusts and nuclear pasta and superfluid oceans. We have watched pulsars sweep their beams across the galaxy and magnetars unleash flares of unimaginable power. We have seen neutron stars collide, forging golden fires that shook spacetime itself. Now it is time to step back and consider what these strange objects mean, not just for physics and astronomy, but for our understanding of existence. What does it mean that the universe contains such things? What does it tell us about reality, that matter can be compressed to nuclear density and remain stable? What should we feel when we contemplate objects that exist on the knife's edge between matter and oblivion? Neutron stars represent limits. They are matter pushed to its extreme, compressed to the highest density possible, while still being matter. One step further, and they become black holes. Regions where matter in any recognizable sense ceases to exist, replaced by pure space-time geometry. The neutron star is the last stand of matter against the ultimate victory of gravity. This limit has a kind of nobility to it. Against forces that would crush it into nothingness, matter resists. Neutron degeneracy pressure, arising from the quantum mechanical refusal of neutrons to occupy the same state, holds back the collapse. Nuclear forces, the residual effect of the strong interaction that binds quarks into protons and neutrons, provide additional support. The star balances on this knife's edge, neither collapsing nor exploding, simply existing in a state of impossible equilibrium. Your own body operates on a similar principle, though at far less extreme conditions. The atoms in your cells maintain their structure because electrons refuse to collapse into nuclei. Quantum mechanics provides the pressure that keeps matter extended, that gives substances their volume, that prevents everything from collapsing into nothing. The same physics operates in neutron stars, just pushed to its ultimate limit. You and a neutron star are governed by the same laws, facing the same forces, just at vastly different scales. Consider what the existence of neutron stars tells us about the universe. Reality is not limited to the gentle conditions of Earth. The laws of physics permit environments of crushing density, immense magnetic fields, temperatures of billions of degrees. These environments are not hypothetical. They are out there right now, throughout the galaxy, throughout the cosmos. The universe contains far more than our everyday experience suggests. This expansion of the possible has philosophical weight. We naturally tend to assume that our local environment represents some kind of norm, that conditions elsewhere are roughly similar to conditions here. Neutron stars remind us that this assumption is false. The conditions on Earth, the temperatures and pressures and fields that feel normal to us, occupy a tiny sliver of what is physically possible. The universe is mostly nothing like Earth. It is mostly empty vacuum, or stellar plasma, or the compressed matter of neutron stars and the bent spacetime of black holes. And yet we can understand these exotic environments. Through mathematics and observation, we can deduce what happens inside a neutron star, even though we can never go there. We can calculate the behavior of matter at densities we can never create. We can predict the gravitational waves from mergers we will never witness up close. The human mind, evolved for tracking fruit and predators on an African savanna, has learned to comprehend conditions utterly unlike anything in its evolutionary history. This is remarkable. It is perhaps the most remarkable thing about human beings. We are small creatures on a small planet, living brief lives in a vast and ancient universe. By all rights, we should know nothing beyond our immediate surroundings. Yet we have deduced the existence of objects thousands of light years away, understood their structure and behavior, used them to test theories about the fundamental nature of reality. The atoms in your body connect you to neutron stars in a direct physical way. The heavy elements produced in neutron star mergers, the gold and platinum and iodine, are in your tissues right now. When two neutron stars collided billions of years ago, they created atoms that would eventually become part of you. You are not separate from the cosmic violence we have discussed. You are a product of it. This connection goes deeper than chemistry. The physical laws that govern neutron stars are the same laws that govern your body. Gravity pulls you toward the Earth's center just as it crushes matter in a neutron star. Electromagnetism holds your molecules together just as it structures the neutron star crust. The strong nuclear force binds the nuclei in your atoms just as it resists compression in neutron star cores. You are subject to the same physics, operating in the same universe, made of the same stuff. Neutron stars do not care about us. They spin indifferently in the darkness, their beams sweeping across empty space, whether anyone watches or not. The universe has no preference for human existence. The laws of physics operate without concern for human welfare or human understanding. If all humans vanished tomorrow, neutron stars would continue spinning, magnetars would continue flaring, mergers would continue forging gold. The cosmos does not need us, and yet we can know it. We can point our telescopes at the sky and collect photons that have traveled for thousands of years. We can build detectors that sense the infinitesimal stretching of space-time as gravitational waves pass through. We can write equations that describe the behavior of matter under conditions we will never experience. This knowing is not required by the universe. It is something we have achieved despite the universe's indifference. There is a kind of defiance in this. The cosmos is vast and old and utterly unconcerned with human existence. But we have carved out a small space for understanding. We have looked at the night sky and asked what those points of light are. We have followed the evidence where it leads, through centuries of observation and theory, until we understood that some of those points are neutron stars, the collapsed cores of dead suns, spinning in the darkness. The universe did not give us this knowledge. We took it. Tonight, as you drift towards sleep, neutron stars are out there doing what they do. Pulsars are sweeping their beams across the galaxy, some of them crossing Earth, some of them missing us entirely. Magnetars are building stress in their crusts, preparing for flares that might come tomorrow or might come in 1,000 years. Binary neutron stars are spiraling closer to their companions, gravitational waves rippling outward, the final merger still centuries or millennia away. Somewhere in the universe, a merger is happening right now. Gold and platinum erupting from the collision, space-time shaking with the impact. None of this requires your attention. The neutron stars will continue whether you think about them or not, but you can think about them. You can hold in your mind, however imperfectly, a picture of these impossible objects. You can understand, at least in outline, how they form and what they are made of and why they matter. This understanding is a gift, perhaps the greatest gift that human intelligence provides. Let the scale of what we have discussed settle over you like a blanket. Teaspoons weighing billions of tons, objects the size of cities containing more mass than the sun, magnetic fields 1,000,000 billion times stronger than Earth's, collisions that forge the gold in your jewelry from the debris of nuclear fire. These are real things. They exist in the same universe you inhabit, governed by the same laws that govern your beating heart and breathing lungs. The neutron stars will still be there tomorrow. The mysteries will still be waiting. The pulsars will still be sweeping their beams. The magnetars will still be building toward their next flare. The binaries will still be spiraling toward their ultimate collision. There is no urgency. You have time. The universe has been doing this for billions of years and will continue for billions more. For now, let the impossible objects rest in your mind as something beautiful and strange. Let the universe be vast and extreme and indifferent, and find peace in that vastness. You have traveled far tonight, from the deaths of massive stars to the forging of gold in cosmic fire, from quantum superfluids to the edge of black hole formation. You have touched the limits of what matter can be. That is enough for one night. The neutron stars will keep spinning. They always do. Rest now, knowing that somewhere out there the impossible exists, and that somehow, against all odds, you can understand it. Good night.